Hello. Good afternoon, everyone. Hope you all had a refreshing break. Next, I would like to welcome Dr. Subhash Joshi to take a session on the design and control of inverter. He is a scientist at the Center for Development of Advanced Computing, Trivandrum. On to you, sir.
Yeah, good afternoon. The screen is visible?
Yes.
Yeah, so the topic is on the design and control of a DC-DC converter, and we are starting from the beginning. We'll start a specification formulation. Then we will move on how we can design a DC-DC converter. Then how the control aspects comes for the DC-DC converter. So these three portions will be covered in this particular topic. So first we'll start with a simple specification. So it's basically a converter which input voltage is at 12 volt and output is around 19.2 volts. Then the output power is around 100 watts. Then let us have a ripple current of the converter. Maximum allowable is around 10% and ripple voltage is around 1%. And the operating frequency is selected as around 50 kilohertz. So in the specification, there are certain parameters are there, like what is a ripple current, what is ripple voltage, all those things. We'll just have a quick look on that. Then we'll go to how to design this converters. So as you know, there are many passive elements exist, like resistors, inductor and capacitors. So these are the three passive elements, which is almost an integral part of any power electronic systems. So when you consider a resistance, we know it is governed by the Ohm's law, and it is basically a scaling of the voltage or current, and there is no shifting and shaping is happening actually. So when you are applying a voltage like 100 volts to a resistor of around 10 ohm, so a current starts flowing. So if you are minutely looking at, the current will be increasing from its 0 ampere and it reaches to some particular current. Like for example, in this particular circuit, reaches to 10 amps, the voltage generated across the resistor becomes 100 volts and is equal to the applied voltage. So it's in summary, basically the amount of current flowing through an element will be such that it is equal and opposite to the generated voltage. So a similar thing we can apply to an inductor also. So an inductor is concerned, it's basically an electromagnetic system actually, like there is an electrical circuit as well as a magnetic circuit. So it's basically a combination of electromagnetic system. So the applied when you are applying a voltage, it is governed by a relation of dLi by dt. And when you are applying a voltage, a flux is generated and the magnetic circuit come in picture actually. So in magnetic circuit, when you consider, it is governed by an equation called d phi by n into d phi by dt. So when you are applying a voltage generated or a back EMF is generated in the inductor, and when these two are equal, then we call it as a system is in the steady state conditions. So when you are making equal, it becomes a n into phi equal to L into I. So the question comes that when you are applying a voltage, we all know that the current is lagging by 90 dB. Then when you when you look on why it is 90 degree, again a question comes. So it's basically comes the magnetic circuit. Like when you are generating a current, a flux is generated, and again to oppose the applied voltage, the flux should be 90 degree displaced from the voltage. So that's again because of that the current is also 90 degree displaced. Now let us see that when you are applying a voltage of 100 volts, a DC voltage to an inductor of 10 millihenry of inductor is that how the current looks like. So when you are applying a voltage, again if you are looking at the same policy, like applied voltage should be equal to the generated voltage. So it means that there should be 100 volts across the inductor. Now we know that to generate 100 volts, again it is same equation will apply that like L into dAbt equal to the applied voltage. So 100 should be equal to 10 millihenry into dAbt. So it means that to maintain a 100 voltage across the inductor, the dAbt should be equal to around 10k. It means that the slope of the current should be equal to constant. So if the slope of the current is constant, then only the generated voltage can be equal to the applied voltage. It means that the current will be continually increasing until either the fuse blows or either the circuit collapses. So it means that in any case the applied voltage and the generated voltage should be equal. If that is the case, then we'll consider three separate cases. We'll consider. So first thing is basically you consider a circuit where you are applying a pulsed voltage instead of a DC voltage. Assume that you are applying a pulsed voltage. Now when you are talking about a pulse, it is having an on period as well as an off period will be there. Now on period, during the on period, assume that voltage is applied across the inductor and of positive voltage, and during the off period, assume that voltage is applied of a negative voltage, like a plus 100 volt as well as a minus 100 volt. Now, when we say a duty ratio equal to 0.5 means the on voltage or the on time as well as the off time are equal. Now, when you are applying a 100 voltage across the inductor plus 100 voltage, as we have seen in the earlier slide, a constant slope will be there of a particular value of 10k. When you are applying a minus 100 volt, again the slope will be the opposite direction of minus 10k. Means that where we started, there will end after one cycle actually. So in this condition, if you see the magnitude of the current basically reaches the same value after the one cycle period. Now assume another case where your duty ratio is higher, like 0.6. It means that on period is larger. Now if on period is larger, then when you are applying a voltage, the current might have reaches to some higher value, and since your off time is smaller, the current will not be reaching to the initial value where it has started. So it means that there will be a rise in the current you can expect after each cycle. Now the same situation we'll see if duty ratio is 0.4. But here actually there's something different, like the current will be decaying, like where we started and where we ended. If you are comparing it, the current will be going to the downward direction. Now we'll find out what is the average value of these three cases. Now when you consider 0.5, the right hand side figure shows when you have a 0.5 duty ratio, the average value will be constant. And when you're having a 0.6 duty ratio, the average value will be going up and going towards positive value. And when we have a duty ratio of 0.4, the average value going downward. So in these three cases, when you see one thing, you can clearly say that when you have an inductor and when you have a pulsed voltage or square wave, then you can achieve any shape of the current with modulating the duty ratio. Like if you have a duty ratio of greater than 0.5, then you can increase the current. When you have a duty ratio of equal to 0.5, you can keep the current at its the same position. And if you have a duty ratio of less than 0.5, your current slope can be made negative. It means that just like you are drawing on a board, like you can go up and go down and you can stay in the same position. So these three things are possible when you have a pulsed voltage and an inductor, when you are applying a pulsed voltage across the inductor with a variable duty ratio. So this is actually shown in this particular figure, where you can see in the right hand side bottom figure, where for some time duty ratio is made 0.6 and sometimes duty ratio is made 0.5 and sometimes it is made 0.4. So you can almost draw a what you call a portion of the sine wave with varying the duty ratio. Now here actually if you see, as I mentioned, when you are applying a voltage, current is rising, and when you are applying negative voltage, current is falling. So in general, if you see any of the power electronic system, when you consider, you cannot achieve the exact thing what you required, but you will be going around that, what you required. Like assume that you required a DC current. So what will be happening basically? A DC current, in average sense you will be achieving a DC current, but in actual sense you will be going around the DC value of that. So that how much you are going up and how much you are going down, that is something like which is called as a ripple actually. So in any passive compound, like it can be an inductor, it is called a ripple current. When you are having a capacitor, it will be a ripple voltage will be appearing. Now in summary, as I mentioned, when you have a pulse to voltage and a variable duty ratio across the inductor, you can have any shape of the current is possible. Any shape of the current you can do it. So an inductor with a switch, like how you can modify the duty ratio is basically a switch actually. So inductor, switch, and a capacitor. If these three elements are there in your hand, you can achieve any shape of current, any magnitude of the current you can achieve it. So so this is basically an introduction of that to just introduce what is duty ratio and what is the ripple and how the inductor works, all those things only. Now we'll go to the actual scenario about our requirement. Like we have a specification of around 12 volt and we need to reach to 19.2 volts. So it means that we require a boost converter, like you have to increase the boost voltage. But the first question comes that how you will design it and a boost converter if you have such a specifications. Now when you need to design, then after the design you require a controller also. So what we'll do basically, we just model the boost converter in totality, and from that we'll extract whatever derivation we got it, and from that we'll design, and when we got the controller design aspects. So in summary, a modeling basically is only a representation of the physical phenomena what is happening by using a mathematical equations. So in the model actually we have a two type of models will be there. One we call it as a steady state model, which will be governing a certain equations of the steady state condition of the system actually. Then we will having a dynamic AC model also will be there, where we'll having a small signal model, like when we have a small variation happening, how the system will behave. So these three things we'll understand one by one actually. So when we have a basic AC modeling approach, various steps will be involved. Like we have to first identify what are the various circuits involved. Then after that we have to eliminate small variations like the ripple, what we call it as a ripple. We have to eliminate the ripple, and then we have to see that when we having a disturbances, how the circuit behaves, and whether we can convert the system in a linear system, because many times a highly nonlinear system analysis will be pretty difficult. So we have to linearize the systems actually. And at the end of the day, we have to make a small signal equivalent circuit, whether it is possible. And if you have equivalent circuit in your hand, then we can easily derive all the transfer function whatever required for the controller design aspects. So in summary, any power system, any converter, if you take it, like either it can be a boost converter or buck converter or any CP converter, whatever, any converter you take it, it can happen three type of disturbances. One is basically the disturbance can come from the input sources like input voltage, or the disturbance can come from the control side, like you may have some duty ratio control will be there. So from the control side there can be a disturbance, or the load itself will be disturbed, like the load can change in sudden, or maybe some transients loads can happen. So these are the three sources of disturbances. Now when you design a converter, we have to consider these three sources based on the priority, or like all three may need to consider, or maybe one of the things may be very important. So based on that, we have to consider these three disturbances. Now each three disturbances will be governed by a transfer function. Like when you have a control output, then control input disturbance when comes, then transfer function will just named it as basically GVD of S. that is nothing but what happens to the output voltage with respect to the duty ratio. That is something like which is people are more looking on. But specifically when you see in general, it's nothing but the output voltage, but all the states. Like whenever take a DC-DC converter, there will be many states are there. When I say states, it means that all the elements which stores the history, just like an inductor or capacitor. Assume that a DC-DC converter is having a two inductors in different places, like a SEPI converter type of thing. Then it means that you have a two states. So how duty ratio affects all the states that need to be identified. Here it's only mentioned the output voltage for the time being. Now another source of input disturbance is basically input voltage. So in that case it will be a ratio of Laplace transformation of the output to the input. And another disturbance will be from the load, then it will be V naught of S divided by I naught of S. So these are the three transfer functions that can happen. So if we can linearize the system, then the total disturbance which can happen in the output voltage, that we can consider it is basically the transfer function due to the control input disturbances multiply the disturbance from the control input as well as input transfer function, then multiplied by the input disturbance as well as the load transfer function multiplied by the load disturbances. So this you can do it because if the system is linear and superposition theorem you can apply it and you will get this particular results. Now, in general, we can say that there can be a disturbance from input voltage that is represented by V in tilde, and there can be a distance from the duty ratio, it is represented by D tilde, and also from the output voltage, like the load change, it is represented by V naught tilde. Yeah, so as we know, a boost converter consists of an inductor and a switch, diode as well as an output capacitor. So a typical diagram is shown in figure. So since the switches are either it is turned on or turned off, based on that two different circuits you will get it. And the circuits are basically like when the switch is in the position 1, which is shown marked in the figure, you will have a two different dynamic equation will be there. Like when the switch is in position 1, inductor is in one side and the capacitor is the other side. So the inductor governs one differential equation which is shown over here. The applied voltage is nothing but equal to L into DIL by dt. And the other side, if you see the capacitor is there also you can see another differential equation will be there, and that is nothing but C into dV naught by dt. That is equal to the load current, like it is again represented by minus V naught divided by R actually. Now assume that switch is in the second position. Now when it is the second position, again we have a two equations will be there. One again governs by the inductor, where the voltage across the inductor is now nothing but the input minus the output, because diode starts conducting it, and input and output voltage difference we can find out, that is nothing but the voltage appearing across the inductor. And in this case basically the current which is flowing through the inductor or through the diode, that will split into two. One portion will go to the capacitor, other portion will go to the load. So again that is again shown in the second differential equation, where you can see that the inductor current subtracted by the load current is nothing but the capacitor current flowing to the capacitor. So these are the dynamic equations which is governing the boost converter. So any converter, when you are getting the first activity is basically find out how many circuits are there, or what are the modes of operation, and write out the dynamic equations. Once dynamic equations are ready, then next question is basically, as the switch, like for example, as the consider the inductor, like when switch is in position 1, as I said, current will be rising. When switch is in position 2, current will be falling. So there will be a ripple in the current where the inductor or current which is flowing through the inductor. Now our interest is basically not on the ripple. Our interest is basically the average sense. So in that case, is whether we can average the inductor current. That's the first question actually. Now for averaging, there will be an on period as well as an off period will be there. So we'll take what are the voltage across the inductor during the on period, which is represented by d of t, and the voltage across the inductor during the off period, that is represented by 1 minus d of t. So just multiply by add it, you will get the average. So while doing this one, effectively what happening is basically your ripple get cancelled actually, and you are getting the average value of the voltage appearing across the inductor. That is what you are getting in the next equations. Now similar you can apply for the capacitor also, like you know what is the current through the capacitor during switch position 1 as well as current through the capacitor during switch position 2. So you multiply it by the current through the capacitor in switch position 1 multiplied by d of t. Then another one the fourth equation, can take it and multiply by 1 minus d. You will get the average value of the current. You can just simplify and you will get the final results what is shown on the right hand side. So after getting the dynamic equations, the next step what we are doing is basically we are finding out the average value of the inductor voltage as well as the capacitor current with the help of the duty ratio. So from the dynamic equations. Now once you get that, next thing is basically if you see this particular earlier equations like the average value of the voltage as well as current through the capacitor, this basically looks like a non-linear equation because we have a two time varying quantities are multiplying together, so it becomes a non-linear equation. So question is that whether we can linearize the equations possible or not. So now to linearize, what we'll do basically, as I mentioned earlier also, we have a three disturbances, like input voltage is getting disturbed as well as duty ratio is getting disturbed and output voltage is disturbed. So we'll just substitute these disturbances and see that what happens to the average value when this disturbances comes. So just substituted these terms in the voltage across the inductor which we are having. Now the voltage becomes a steady state condition as well as a disturbed conditions. All disturbed conditions are represented by cap, like tilde, like VL, capital VL plus VL cap of T. VL cap of T is nothing but the disturbance happened in the inductor when there is a disturbance in either input voltage or load or in the controller inputs. So in that condition, whatever quantities are there, like the duty ratio D becomes D plus D cap of T, input voltage becomes input voltage plus input voltage cap of T, as well as the output voltage also becomes output voltage and V naught cap of T. So these all disturbance you can substitute, then finally you will get what are the steady state as well as the disturbance quantities in the inductor voltage. And you can simplify further, like while simplifying one thing we can consider that when you have two disturbances, like for example duty ratio cap of T as well as input voltage cap of T, when you are multiplying together, we can see that or we are neglecting these two terms, considering that disturbances are small quantities and when two disturbances are there, this product will be much smaller and its influence will be very small. So in that context, we can neglect these two or neglect when two quantities are there. Like for example, the first term like D plus D cap of T multiplied by Vn plus Vn cap of T. In that condition, after multiplication, we have only three terms. Like D and Vn will be there, then D and Vn cap will be there, then D cap and Vn will be there. So we will be neglecting a D cap and Vn cap. This term will be neglected. So you can write down these equations which is shown in the bottom of the or second equations. Now after that, after cancelling and whatever eliminations are required, if you are doing this one, you will get the third equations, which consists of, when you look on third equation, so you can see that the first two terms nothing but a steady state conditions and the last three terms are governing by the small signal, like what are the disturbance happening. And left hand side also we have a steady state conditions of VL as well as a small signal conditions over. So we can compare the steady state and small signal terms and which is given in the next line, like the next equations. So in steady state equations, the voltage across the inductor is nothing but comparing the left and right hand side, Vn minus 1 minus D into V naught. So we have seen in the earlier slides that when you have a voltage across the inductor, it means that the current will be continually rising. So when a converter works in a steady state, in that condition, the current or the average current through the inductor or average current of the inductor will be constant. It will be a same like a DC quantity. It will be DC quantity. So in that condition, the VL, average value of VL, which should be equal to 0. So we can substitute that equal to 0, and finally you will get a steady state equation like V naught, that's output voltage. Take a steady state output voltage is equal to steady state input voltage divided by 1 minus duty ratio. And we can compare the varying quantity like a small signal quantity in the left and right hand side also, and you will get the equations which is shown in the bottom of the slides. You will get it. Now the similar thing you can apply for the capacitor current also. So we have already written the average value of the capacitor current, and that is shown in the first equation. So here also we will give a disturbance, like output voltage is getting disturbed, duty ratio is getting disturbed, as well as the inductor current will be getting disturbed due to the disturbance of the duty ratio as well as the input voltage on output voltage. So we can substitute V naught equal to the steady state voltage as well as the disturbed voltage, and duty ratio also equal to steady state as well as disturbed, and inductor also the same thing we can write down. So here also when you simplify it, again you have to eliminate the two varying quantities which are multiplying together, and you can simplify the equations. So you will get the third equation where you can see that right hand side you can see that there is a steady state quantities are there, like minus V naught by R plus 1 minus K into ILA, and after that whatever you are seeing is basically a small signal quantities which are erased due to the disturbances. It can be either from the duty ratio or input voltage or from the load. So these things, if you see left hand side also there is a steady state quantity, you can compare with the right hand side. So you will get the capacitor current, like a steady state capacitor current, that should be equal to C into dU by dt, which is equal to minus V naught by R plus 1 minus D into IL. So in steady state the current through the capacitor should be equal to 0. Because if you have a in steady state, if you have a DC current through the capacitor, it means that the capacitor voltage will be continually increasing. So in steady state it will not be taking place. So in average sense, IC should be equal to 0 in steady state. So you can equate that and you will get a relation which is connecting IL and V naught by R, where V naught is nothing but we have seen in the earlier slide, V naught equal to Vn by 1 minus K. You can substitute over here, and you will get a relation of between the input voltage as well as the input current. IL is nothing but the input current for the boost converters. Now similarly you can compare the left hand side small signal as well as right hand side small signal. You will get a governing equation which is connecting the capacitor current as well as the disturbed properties like output voltage, duty ratio, and inductor current. So in summary, actually we are having a now from this point we will just leave the steady state and we will just move on to the small signal to understand how the transfer function looks like and how you can design the controllers and other things. And then later we will back to the steady state, and for the design of the boost converter we will do it. So we have now two small signal equations we got it. One related to the inductor, that is L into dA by dt is equal to Vn minus 1 minus D into V naught plus D cap into V naught. And another equation will be C into dV by dt equal to minus V naught by R plus 1 minus V into IL minus D cap into IL. So when you see the first equation, say we can it's become again a linear circuits. It becomes because all the non-linearity we just removed because of multiplication of two non-linear components. All those things we did, and finally we removed the non-linearity component, and finally we got a linear system. Actually, I cannot say it is a linear system. It's a dependent source also will be the circuits. So we can write or we can draw a circuit. Say like you have a source Vn, then from that there will be an inductor, which will through the inductor there is a current IL will be going, and there will be a drop L into dA by dt. Then after that you have a source like V naught, where we have a V naught into 1 minus D term will be there, and then we have another source will be there, which is again V naught into D cap, where we'll write V naught into D cap in series with that, where it is the disturbed quantity only it is there, where 1 minus D is nothing but the steady state duty ratio, which we will be putting into the right hand side, and it is basically shown as a in a square. It is shown there actually 1 minus D into D cap. Now the second also we can write down an equation where only thing is basically this is current related circuits. So we have a current source will be there in the picture, So it is nothing but 1 minus d into IL cap. We'll represent as a current source. Then there will be a sinking source will be there, IL into D cap. Then there is a capacitance related component will be there, C into dV naught by dt, where V naught is the output voltage, and there will be a current V naught by R will be there, the secondary. Now, when you see these two circuits, you can see one point you can correlate. Like in the first circuit, right hand side you can see a source which is nothing but 1 minus V into V naught, where V naught is nothing but the output voltage of the second circuit. So it means that and again, if you see the second circuit in the a current source in the second, it is nothing but 1 minus d into IL, where what is IL? IL is nothing but the current in the first circuit. So the first circuit current is linked with the second circuit through a term 1 minus d, as well as the second circuit voltage is linked with the first circuit voltage with a term again 1 minus d. It means that this can be clubbed together by considering it is a transformer of turns ratio 1 minus d is to 1. So these two circuits can be are connected together through a transformer, and the turns ratio of the transformer is nothing but 1 minus d is to 1. Like primary will be having a turns of 1 minus d, and secondary will be having a turns of 1. This is basically a fictitious transformer. So finally, we can say that the small signal modular boost converter consists of a source V with an inductor and a DC source of V naught into D delta, and a transformer having a turns ratio 1 minus D, and a current source will be the secondary, and the capacitor as well as a resistor giving an output voltage. So now this circuit is become a very simple circuit. There is no switches not involved, and you can derive any transfer function from this particular circuit. So we'll just proceed further and see how the transfer function can be derived. So for the time being, for this particular session, we will derive the transfer function between the control as well as the output, as well as control as well as the input current, because these two are the state variables. Like when you see the circuits, you have a output capacitance will be there, which is one of the state, and the input inductor will be there, that is another state. So we'll derive all the control relations which is connecting the duty ratio with the states will be derived. So so considering that the input disturbance will not be considering in this session, so we made input disturbance equal to 0. So when input disturbance are 0 means that in the circuit left hand side source will be shorted. Now, so in that condition, now we can bring the left hand side component, like you have an inductor and as well as a source will be there. These two components you can bring it right hand side, like any transformers, you can have a parameter transformation from a secondary to primary or primary to secondary is possible, and is governed by the turns ratio. So the current IL, if it is taken to the secondary, it is multiplied by the turns ratio 1 minus d, and the voltage source, which is the V naught into D cap of T, will be divided by 1 minus d. So the voltage source will be coming to the secondary, and the inductor will be there. Now what is the inductance value? Inductance value again it is divided by 1 minus d square. That is the inductance value division will be there. So the voltage source inductor will be taken into the secondary side. Then the remaining components will be there itself. Like you have a current source, then you have a capacitor and resistor, which is there in the secondary as it is. Now, so now actually what we require is basically we need to derive the transfer function of this particular circuit, which is connecting V naught as well as duty ratio. Now here actually you have two sources, and the circuit is basically a linear circuit. So you can apply the superposition theorem. So in the left hand side circuit, you can see where the current source is considered as an open circuit. Then the circuit is only a voltage source, inductor as well as a capacitor and resistor. Then the right hand side, if you see, the voltage source is basically so the voltage source is considered as a short circuit. Then the inductor comes in parallel with the capacitor as well as the resistor, and you have a current source in the picture also. So in the left hand side, you can find out what is the relation connecting V naught as well as the duty ratio. Like it's just like an impedance, like this is a voltage divider circuit. Here the R and C will be in parallel, and in series with the inductor will be there. So input voltage so you can find out the voltage appearing across the R and C divided by the total applied voltage. and that if you do it, you will get the V naught as well as the duty ratio will come in picture, and you can solve these equations to get the V naught and the duty ratio. And yeah, so this is the relation which you are getting. Now actually if you see some from steady state actually we already find out some terms like V naught equal to V in by 1 minus D, as well as IL equal to V in by 1 minus D whole squared divided by R. So these two relations we already got in the earlier circuits, actually earlier steady state relations. This you can substitute over here, and you can finally simplify V naught by D tilde is nothing but V into 1 minus D whole squared. Then there is a numerator term as well as a denominator term will be there. So we'll be closely looking on what is this numerator and denominator term when the later slides when it comes, actually, because there are some special things are there. Like I can hint over there, like if you see the transfer function, the right hand side, it is having a 0 on the right hand side is appearing, like it is 1 minus S into L divided by R 1 minus D. So there is a 0 in the right hand side, whole zero structure will be there. Now come to the control to the input, now we'll see how the input current looks like. Now when you say input current, the same circuit will look on the things, only the difference comes that here actually the IL, which is the current in the primary, when it transferred to the secondary, it is represented by IL prime, but all of them remain same. Only thing is basically you have to find out the relation between the input current as well as the duty ratio. So when you need to find out the input current duty ratio, the output voltage is not there in the picture. So you can just simplify again, the circuit is remain same. Only thing is basically you have to find out how much current is flowing through the primary. So for that, in the left hand side, it's only you have to voltage, you have to divide by the total impedance, like C in parallel with R, then in series with the inductance. So you find out the total impedance, and the voltage you divide with the impedance, you will get the primary current. Now in the secondary second circuit, actually something different, where you have to find out what is the current flowing through the inductor from the total current source. So these two things, if you add it together like superimposing, you will get the total current through the inductor, which is referred to the primary, referred to the secondary. So in the first circuit, you will get IL prime divided by D tilde, you will get the relation which is shown in here. And the secondary and the second relation is nothing but related to the second circuit. Again, you can find out IL tilde, I2 tilde divided by D cap. You can add it together, and to bring it to the primary side, divide by 1 minus D, you will get the total transfer function in the primary, referred to the primary with respect to the states. So you have a duty ratio related to the input, inductor current, input current, referred to the state. So here also, if you see, there is again there is a 0 in the numerator existing, and when you compare this denominator, that as we know, it is the characterization of the system, so it is remain same actually. So any converter, if you see, denominator will be remain same, because that decides the character of the system, and it will be same for one converter. Like boost converter will be same if you are referring to any states, like it's an inductor or capacitor, it will be remain same actually. Yeah, so now with this understanding of the transfer function, we'll just again go back to the steady state, then we'll be back to the transfer function again to understand how we can design the PI controllers and other things. So in the first thing, actually we'll just look on steady state relations, like yeah, so we got some of the steady state relations, like V naught is nothing but V divided by 1 minus D. Then another relation which we got is basically IL is equal to I naught divided by 1 minus D. And again input voltage, input current relation also we found. So from the, when you look on the input voltage, input current relation, one thing which you can see that input voltage is divided by 1 minus D whole squared into R, that gives the input current. It means that R is nothing but the load resistance. So when the switches are on and off happening, like modulation of the switches are happening, the resistance is not directly reflecting as such in the input side. It is nothing but the resistance multiplied by 1 minus D square. It is appearing as the input impedance. So effective input impedance is nothing but 1 minus D whole square into R. That is the effective input impedance. Right. So now we'll from this steady state relations, we'll find out how we can design the inductor and the capacitor for the given specifications. So as you have seen the right hand side, as I mentioned, the ripple is nothing but the peak current, like there will be a bottom of the current as well as a top of the current. The difference in the peak to peak difference value gives the ripple actually. So when you are applying a positive voltage Vn through across an inductor, the Vn by L into dTs. dTs nothing but the ratio, like the how much time you are Vn voltage is applied. So that gives you the delta I. Like when you are applying a DC voltage, current starts increasing, as I mentioned. Now the amount of increase in current is nothing but the applied voltage divided by inductance and multiplied by the time duration for which the voltage is applied. Right. Now the ripple is generally it is represented as a percentage of the average current. So we will divide the delta IL by IL. And IL, anyway, we have seen the earlier diagram that IL represented by Vn divided by 1 minus d squared into R. So you can substitute over here and Vn will get cancelled, and finally you will get a relation which is connecting the ripple voltage, like percentage of ripple is equal to 1 minus d whole square into d into ds into R divided by L actually. So here if you are looking, you can see that there is a product which is d into 1 minus d whole square is also appearing in the ripple. So from this one you can find out the inductance value. So if you know the duty ratio, then and also the operating frequency and load resistance, and also how much percentage of ripple is allowed, then you can find out the inductance value. Now similarly you can compute what is the capacitance value is requirement. Again, as I mentioned, the capacitance ripple again due to the on end of the switch is happening. Like for example, when switch is in the on position, the capacitor will be discharging. So until that the capacitor will be charged completely. When switch is in the position 1, the capacitor starts discharging from its positive peak towards the negative peak. So during this period, like the diagram which is shown over here, whatever current is discharged by the capacitor, that will be reducing capacitor voltage from the top peak to the bottom actually. So we can say that assume that the load current is constant, that is nothing but I naught. Then when there is a constant current is drawn from the capacitor, and if C is the capacitance value for a time dTs, that gives you the delta V. It is nothing but from the relation C into dV by dt is nothing but the current flowing through the capacitor actually. So this again the ripple in the capacitor is again represented by the average voltage. So you can divide by V naught. So when you divide it, you have a top term I naught and bottom term V naught will be there. So you can V naught by I naught is nothing but the output resistances. So you can simplify these relations, and capacitance you can take in the left hand side. Then you can get a relation dTs divided by R into delta Vc divided by V naught. So this is represents the capacitance requirement for of 10% and a ripple current of 10% and ripple output voltage of 1%, and assume that operating frequency is 50 Hz. Now as you know, the duty ratio is nothing but we have a relation, we already derived a relation which is connecting the input voltage and output voltage. From that you can find out what is the steady state duty ratio requirement. So you will get a steady state duty ratio is nothing but 0.375. Now load resistance is nothing but V naught squared by P naught, which is around P naught, you know, it is given the specification. P naught is also given the specification. You can find out what is the load resistance, which is around 3.68 ohm. Now inductance you can compute from the ripple actually, as I mentioned. D anyway you already computed. TS is nothing but frequency, you know, 50 kilohertz. So TS is nothing but 1 by 50 kilohertz. Then resistance already you computed. Then delta IL by I naught, which is already given as 10%. So we'll take it as a 0.1, and you can solve this inductance value. You will get around 108 microhenry. Now capacitance also D anyway you got it. TS is nothing but 1 by 50 kilohertz, and R anyway you computed. Then delta Vc by V naught, that is nothing but it is given as around 1%. So you can substitute over here and you can get the capacitance value. Now question is that whether these numbers are right. So we need to validate this one. So we can have a simulation. We can use any package. Here actually we used a package called PCM actually. and this is the boost converter is simulated, and you can see that it is reaching to a steady state voltage which is required around 19.2 volts is the output voltage which is required, and it is reaching to 19.2 volts after a certain time. So here we can see that it is reaching to 19.2 volts around after a 7 millisecond, and the peak voltage is reaching to 24 volts. So after a overshoot, only it is reaching to 19.2 volts. And again, this is without any controllers, like in open. This in the open loop it is working actually. Now let us see how the current waveform looks like. Yeah, before that we'll see what is the ripple actually, whether it is matching with our requirement. So the ripple is taken from the in the steady state condition we can expand that waveform, and once you expand it you can see this triangle type of thing where the peak to peak ripple comes around 0.1903 and 19.17 is average voltage. When you do it, you will get around close to 1%, which is the required specifications. So the selection of the capacitance is matched with the required ripple voltage specification. Now the inductor current, if you see again, inductor current reaches to a maximum value of 17 ampere it is reaching, and the steady state comes around 8.2 or 8.3 ampere, and reaches again after 7 millisecond. So in both of this case, you can see that the circuit is working in the upper loop condition, like mixed or closed loop controls are not there, and it gives a larger overshoot as well as a larger setting time is required to work with the boost converters. And the ripple current, if you see, you can expand it and see that peak to peak ripple current is around 0.8301 and the average current is 8.3, and when you do the division you can get that the peak to peak ripple comes around 10% peak to peak ripple is there. So the selection of inductance is also matching with the requirement. So the steady state equation we have taken, and we did the calculation for inductance and capacitance, and the simulation matches with the model as well as with the chosen value of capacitance as well as inductance component. But only thing is basically, even though we run the system, we found that it is having a larger overshoot as well as settling time. Now how you can solve this one? So there only what we arrived with the transfer function we have mentioned. We'll just go through the transfer function and see that whether we can solve this issue or not. So when we look on the bot plot of the system, like we have already derived the transfer function equations for the output voltage. This is the output voltage connecting the duty ratio, and where if you see all the relations, it is the value like R, D, duty ratio, L, C, all components are now known to us actually. You can substitute all the values and you can find out exactly what is V0 and V0 by D cap. And similarly, you can find out what is IL by D cap by substituting whatever parameter which you have already designed. And you will get a transfer function which is shown in the bottom of this particular slides, where after substituting all parameters, and you can draw the bot plot of this particular transfer function. And for drawing the bot plot, we used a simulation package called Scilab. It is an open source package. And here actually when you compare it, what you can see that there is a resonance. That is one thing which you can observe from the bot plot actually. And resonance occurs close to around 700 hertz, also around 700 hertz resonance occurs. Now from this transfer function which is in the bottom of this one, you can see that the denominator is consists of a second order system. So when you have a second order system, then you can solve this rules. You can find out that there is a complex conjugate is appearing, and that leads to a resonance. And resonance frequency in omega, it is nothing but 4210. So when you divide it by 2 pi, you will get the resonance frequency in hertz, and the plot is also given in hertz actually. Now after the resonance, actually what happened is basically you have a right hand side 0 is there, which is appearing at 13050 frequency, and when you divide by 2 pi, you will get something around 2.2 kilohertz, 2.2 hertz actually, 2.2 kilohertz. The 0 will appearing actually. Now what is right hand side 0? Right hand side 0 when you see, or this particular transfer function when you are seeing, like 1 minus s into tau, or 1 minus s by omega, when you are considering its magnitude is same as, like for example, you consider a transfer function of 1 plus S and 1 minus S. So magnitude of 1 plus S is same as 1 minus S, because magnitude, while computing the magnitude, you are squaring and adding it. So the negative will not influence that. So both the right hand side and the left hand side 0 will give the same magnitude if the coefficients are remain same actually. Only thing is basically both are giving 20 dB per decade in the increasing sense to give that. But right hand side 0, if you see, since it's having a negative, it gives a phase angle plot of minus 45 degrees and degree per decade. But if you see the left hand side, it gives a plus 45 degree per decade. So what happened is basically in the right hand side 0, if you are considering, the magnitude will be 20 dB per decade, as well as your phase plot will be minus 45 degree per decade. So whatever existing in your circuits, in that particular circuits, it will push the gain plot to the higher level, because it is having a 20 dB per decade, and phase plot to the lower level. It means that the gain crossover frequency, it will push towards the right, and phase plot, it will push to the minus 180 degree very early. So all the right hand side 0 can leads to a unstable system actually. So that's why people are too cautious about right hand side zeros. Okay, anyway, so we can see over here that like initially after the resonance you have 40 dB per decade, but when the 0 comes, and that is the second red dotted line, you can see when the 0 comes in picture, it becomes 20 dB per decade, and it going as it is. And also you can see that there is because of this 0, the finally the angle reaches to minus 270 degree also it is reaching. Now the gain crossover frequency is shown by the third line, which is where the gain crosses 0 dB, and you can see that during the gain crossover frequency you have minus 250 degree phase angle is there, and which is unstable actually if you are closing the loop. Now let us see how the inductor current disturbances or looks like with the duty ratio. So you can consider this transfer function, or you can substitute all the values, and you can plot the mode plot. There also you can see that there is a resonance because it is the characteristics of the system. And here actually there is a pole which is 2664 omega, and which is slightly the left hand side. And again gain crossover we are looking at, which is appearing the third line, where you can see that in any case your phase angle is not reaching to minus 180 degree, and the system is very stable actually in that sense. Now question is basically you have seen that there is a larger overshoot in the voltage as well as the current. How you can reduce it? So the one option is basically you can add a PI controller. Now the general equation for the PI controller is shown over here. There is a gain will be there, then there is a pole will be there, S, and there is a 0 will be there, 1 plus S by omega. So if this particular PI controller, if you are seeing, you can see that there is initially there will be a minus 20 dB per decade slope will be there due to the S actually, and till it reaches to omega 1, and where it becomes 0, because then numerator 0 will come in picture. And omega generally will choose basically above resonance will choose it, so that overall gain of resonance is less than 0 dB. So here actually if you see, one of the thing what we can do here actually, that here if you see over here, you can see that resonance is basically well above 0 dB. So it means that the resonance point gives a larger gain, and when you are closing the closed loop, like you are closing the loop, there is a chance that the resonance can give you an issue actually due to the or driving into the unstable situation. So it is better that you can reduce the gain at the resonance to less than 0 dB. Now for that the easiest thing is basically you can push this pole, like on the omega 1, you can keep it above resonance, because by that time 1 by S term will be there, which is minus 20 dB per decade. It will push all the gain plot to the below 0 dB, because of it is going to the negative direction actually. So you can choose, in such case let us choose the omega 1 such as 10,000. 10,000 is basically above the resonant point, and you can connect this PI controller to the main circuit. So this is a typical diagram of PI controller alone, where you can see that there is a minus 20 dB per decade initially coming up, and there is a phase margin will be there, like a phase plot will be there, which is starting from minus 90 and going into the 0 actually. So when you connect this one, whatever original diagram will be there, like this is the original plot, where initially when you have minus 20 dB per decade, means that from a 0 plot where this a constant plot will be there, that is pushing downward by minus 20. All the term will be minus 20 will be pushing downward, and phase also will be pushing downward by around minus 90 degree as the frequency is increasing. So this is a typical circuit which is shown over here, where a PI control is applied and output voltage is taken and fed back and compared with the references, and devices are turned on and turned off based on the modulated signal or output of the PI controllers. So after connecting the converter, what we can see basically, there's a PI controller will be there, and like the first two terms related to the PI controller, and the last term related to the boost converter V0 tilde divided by D tilde cap actually. So the overall boot plot is shown over here, and the overall boot plot is also drawn over here. So what you can see basically, the resonant point now it is pushed below 0 dB. So since it is pushed below 0 dB, we can it will not give much it will not be it will work to a stable system. And also gain crossover frequency, when you see at gain crossover frequency, the maximum phase angle is only minus 90 degrees, so you have a phase margin of around 90 degree phase margin exists actually. And for all other things, gain is less than unity, so it gives a stable system. We get a stable system. Now with this one, we'll just plot how our output voltage looks like with the PI controller. So you can see the output voltage is shown over here. But one issue is slowly noted is basically earlier the output voltage was reaching at 7 millisecond, and now it is reaching only at 14 millisecond, which is one of the issue. But overshoot is eliminated. Like earlier, the voltage was going around 25 or 26 volt, now it is not going at all. So our voltage is reduced, and the current also, when you see the current also, it's not having any over current shooting is not there, but it is having a larger steady state. Time is required for reaching the steady state, a lot of time is required. Then let us see that whether this can be eliminated or not. So instead of that, in addition to the voltage controller, we can put a current controller also, because anyway it is required in a circuit, like we need to control all the states actually, like it's an output it's a capacitor or it is an inductor. Whenever there is inductor and capacitor is there, it is always advisable to control the states using the feedback. So this is considered over here. So current is taken and fed back over here. So in that condition, again we'll see how we can solve this one with our small signal model which is existing in our hand. Now the circuit will be looks like this one. You have a error will be there, which there is a PI will be there. That PI is nothing but the voltage controller PI, and that will be fed back to the summer. And inside the summer, whatever you are seeing is basically a current PI will be there, and you have a IL by D cap, which is nothing but the small signal transformation is already derived, like how the IL, like inductor current or input current, varies with the duty ratio that we already derived. And finally you are getting a IL cap, you will get it. Now that you can multiply with the V0 cap into IL and to get the V0. Now how you will get V0 cap by IL cap? Anyway, we already derived V0 cap by D cap duty ratio, as well as IL cap by duty ratio is there in our hand. We can divide it together to get the transformation of V0 cap by IL cap. We can get it. And yeah, so this is the overall system will be there. So you can while now two PI controller comes in picture. So now you have to derive the PI constant for the current controller as well as for the voltage controller. So during this one only you have to keep in sure that a few points will be very important. One is basically you ensure that the gain plot always crosses 0 dB at minus 20 dB per decade. If that happens, it ensures a phase margin close to minus 90 degree, but that may not be exactly minus 90 degree, because there may be some other nearby poles and zeros will be existing. So because of that, it may not be exactly minus 90 degree, but still you can ensure that it is not too far from 90 degree actually. Now, another point which you have to consider basically the settling and transient overshoot, if you are seeing that depends upon the 0 dB crossover frequency and as well as the phase margin. So, like the settling time, it depends upon the 0 crossover frequency, and transient overshoot is nothing represented by the phase margin. Now, settling time is roughly calculated as 3 divided by omega c to 4 divided by omega c seconds. That will be the settling time. So, you have to choose omega c such that the settling time, if any requirement is there, it is meeting the required specifications. Now, overshoot, if you are looking, as I mentioned, it is depend on the phase margin. So, if you have a 30-degree phase margin, you can expect around 37% overshoot. If you have a 45-degree phase margin, you can expect around 16% overshoot. And if you have a 60-degree phase margin, you can expect around 1% overshoot. Consider these aspects, you can choose the PI controllers. So finally, the overall system, when you see the PI controller like IL cap divided by like the current states of the current divided by the error. That transfer function, when you see, this will be the mode plot of the transfer function. And here you can see that at the crossover frequency, you have a sufficient phase margin is there because total phase is less than minus 90 only. And the resonant point is almost diminished, like at 20 dB per decade only, it is crossing the 0 dB actually. Now the overall system, like mode plot of the output voltage, if you are seeing, then you can see that again at the gate crossover frequency, it is around 20 dB per decade only it is coming in. And during the gate crossover frequency, you have a angle around 120 degree around, and you have a phase margin of 60 degree phase margin is there. And where 60 degree, we are expecting only 1% or less than 1% overshoot only we are expecting. And gain crossover is occurred at 170 hertz. It means that around 1070 radian per second. So settling time will be around between 2.8 millisecond to 3.7 millisecond. Now this is the input current. Finally we got it. So we got a settling time around, when you look on, it comes around 3 millisecond, which is as per the expected. And overshoot is also close to 0 actually. Only very slight overshoot we can observe in the current actually. And this is the output voltage. Finally we got it, where you have a settling time close to around 3 millisecond itself, and overshoot will be close to 0. So in summary, actually, what we did is basically we took a boost converter, and we have derived the modes of the operation of the boost converter, and from that the dynamic equations we derived, and from the dynamic equations we come up with the steady state as well as small signal models, which is the equations connecting steady state we derived, then the equations connecting the small signal model we derived, and try to link that small signal equations with a circuit so that we can easily come up with the transfer functions. So there are many modeling methods are there. This is one of the modeling methods people are generally
So Subhash, let's wait for questions. Oh, it appears Subhash went offline. Network issues maybe. Hmm.
Hello, Dr. Sadeep, are you available?
Yes, Jason. Yeah.
Yes. Subhash went offline or?
I think he's showing no battery. Maybe he's connecting his charger. Maybe I'll just ask him to reconnect. Okay.
Yeah.
Just give me a second.
All right. Okay. Hello.
Yes, hi.
Oh, hi.
Sorry, this is actually today severe network issue are there in the office. Sorry. Yeah. So that's about that first part of the presentation actually related to the DC converters design and other aspects. So these are the books you can refer. That's one of the this book is basically Erickson's and Max Chip. Probably that is another thing which is largely describing all these aspects. Yeah. So any questions in this particular session? We'll answer that.
Yeah. So one question is that when we talk about DC-DC converter for an electric vehicle, now we have multiple operating points. So here you have discussed on one operating point and how we can reach an optimal design. So, what is the methodology that we will use for an electric vehicle now? And the obvious answer is to go through all the operating points and then find an optimum capacitor size or an inductor size. But are there other tricks that you could use to reach such a value also.
Yeah. So any design like electric vehicle or whatever the design, only the first important thing is basically identifying the operating conditions. That is something like another biggest task actually, because normal operating condition actually you can easily understandable, like it's a laboratory type of operating conditions. But when it goes to the actual field, there will be the operating conditions which will be beyond some of our understanding. It's a power system or like it's electric vehicle. There will be many situations will be there where we may not be able to identify scenario earlier also that can happen actually. But the people are working on that, and many things they are driving on that. So when you are designing an inductor or capacitor, the important thing which you have to see that under all these operating conditions, which is more stressing, or which is more giving a more stress to this capacitor or inductor, that the stressed operating condition is something like which is important. For example, I can say that when you are choosing a capacitor, the capacitor is mainly two things or many parameters are influencing the capacitor. For example, a capacitance value, if you see, that is governed by the operating frequency, it is governed by the DC voltage, applied DC voltage. So we have to see that in the operating conditions, what is the maximum DC voltage can appear in the capacitor, or what is the maximum operating frequency that can come, because sometimes it's a fixed operating frequency, then it's okay. But if it is a variable operating frequency, then you have to see that what can be the maximum operating frequency can appear. So based on that, you have to choose what is the whether the capacitance which you have chosen, that capacitance value will give the same value at the particular operating frequency also. Because many times capacitance value degrades by around 20% or 30% when you have a larger operating conditions. So that you have to consider. So in nutshell, what I mean basically, you may have many operating conditions, but you have to identify the operating condition which gives more stress to the parameters or the components. And that operating condition you have to choose for the selection of this capacitor as well as the vector. Yeah.
Okay, thank you for that answer.
Any other question?
I don't see any other question.
Yeah. So we'll move to the second topic then. That is mainly on.
We'll take a 5-minute break and then move to the next topic.
Yeah, we'll take a 5-minute break then. Yeah, we'll make it.
Yes. Okay, perfect. We'll take a 5-minute break and then we'll move to the next. Yeah. Okay. All right.
Hello, Dr. Subhash. I think we can start now.
Yeah. Yeah, right.
Okay, perfect.
So the next portion is basically design of a single phase inverter. And with the understanding of DC converter, now we'll see some portion of theory portion we can move to, or we already covered the DC converter, may be useful in this portion also. But again, the scenario is different. The first one was basically your operating conditions were DC, and now your operating condition become AC actually. So how you can handle these situations? We'll just work on this. So as we know that when you consider a inverter, basically I can say a typical inverter is shown over here actually, where you have a 4 switches and a single phase inverter. You have a DC source will be there, and it is feeding to, assume that it is connected to the grid, like for example, this vehicle to grid, all those applications are coming where you are connecting the battery to the grid actually. So maybe you can consider a typical application, such application you can consider here also. So you have a DC source, then you have switches, HVAC is there, then you have an inductor and a grid is there. Now in this particular scenario, how your inductor can be designed, or the ripple, how the ripple will be there for the inductor. So that's again a question comes, because DC converter was bit easy because you have a DC quantities, right? So again the relation, the Werning relations are remain same, like that's in inductance multiplied by the ripple divided by the on period. That is nothing but should be equal to the voltage applied across the inductor. That is that relation is unique for any circuits. So here only difference is basically the applied voltage across the inductor, like voltage across AB. If you are seeing it may be VDC or minus VDC. Let us take a typical scenario of plus VDC itself. And at that condition, your grid voltage will be a sinusoidally varying quantity, and also it can take any values because it is a the switches we are expecting it is operating at something around 10 kilohertz or more than that, and your grid frequency will be 50 hertz. So in that condition, the plus VDC can appear in the positive side of the grid voltage as also in the negative side of the grid voltage. So any scenario it can take it actually. So in general equation it is shown over here, like inductance into peak to peak ripple divided by on time. It's nothing but a DC voltage minus the grid voltage. Now the on time, when you are considering an accepted chain, it can operate either it's a bipolar operation or it can be a unipolar operation. Any operation is possible actually. So here it is assumed that the switch is operating a unipolar operation due to many advantages which we are having in unipolar modulation. If that assume that the H bridge is operating in the unipolar modulation method. So in that condition, effective switching frequency appearing across switch across AB is nothing but 2 times FSM. So in that condition, the on time is nothing but your modulated signal divided by 2 times FSM. So you can substitute this on the top, and you can find out the peak ripple is nothing but VDC minus V sin omega t divided by 2 times L into Fs into modulation. Now here actually one difficulty what we can see basically here, ripple itself is a varying quantity now. So earlier actually we had a constant quantity for the ripple. Now ripple, if you see, it's again a time dependent quantity, and time dependent on the grid voltage or grid voltage profile, as well as time dependent on the modulated signal profile also. Now question comes how you can find out the modulated signal of the circuits. Now the modulated signal, when you look on here, for example, it is the inverter assume that it is delivering a current of I, like I equal to I sin omega t minus theta. So in that condition, the voltage appearing across AB is nothing but the grid voltage plus voltage drop across the inductance. Now, if L is the inductance, you can find out the voltage drop across the inductance. You can add with the grid voltage to get the total voltage across the AB. You can find out. Now you can divide it by the VDC to get the modulate signal, and the modulate signal is given over here, which is the ratio of voltage V by VDC sin omega t minus omega L divided by VDC into cos omega t minus theta. That will be the modulate signal. You can substitute it back in the earlier equations of ripple, and you can get a relation of it. So here you can see that now it becomes depend upon only on the omega t part will be there, but also it depends on theta also, like phase angle theta will be there in the picture actually. So now the ripple is basically become a trivial number actually, where how we can find out the ripple, like for example how you can solve the equations, because the ripple itself become a very important thing now actually. So the question is basically in entire operating profile of the grid voltage where the maximum ripple can appear. So that we have to identify, and that should be within the limited specifications, because in the sin omega t curve there may be a place where minimum ripple will be there, there may be a place where larger ripple will be there. So we have to identify which is the place where larger ripple occurs, and from that only we have to find out the inductance value requirement for the converters. So to understand that the maximum ripple, to find out, just differentiate the maximum point and equate to 0. That is something like which we can do it. So that is shown over here. Now here actually the equations become pretty complex equations. And one of the method which you can apply is basically you can take some of the typical cases and you can substitute over here and find out any typical features or typical points which you can identify from that particular curve. You can find out. For example, I will take about a single phase converter of something around 10 kVA, a grid voltage of around 240 volts. And the rated current issue that is around 60 ampere, and inductance of value something from 1.8 millihenry we will choose for this particular understanding. And DC voltage of 475 volt also is considered, and different power factor angle we considered, like 0 degree, 30, 60 and 90 degree. Only thing is basically why this different power factor angle, because we found that the ripple is dependent upon sin theta actually. So we'll understand that how it comes in picture. Now also the inductance value function we also will find out, like we'll choose an inductance value 1.8 millihenry, and we'll do a plot for 60 ampere as well as 0 ampere for all power factor angle, as well as then we'll make the inductance half, then again we'll draw for plot for 60 ampere and 0 ampere for all power factor angle, and we'll increase the inductance twice and we'll do the same, and DC voltage also will reduce it slightly, and we'll find out any effect is there. So for example, if you consider this particular curve, you can see that for the chosen value 1.8 millihenry, we found that with a different value of theta, the curve is plotted over here. So you can see that the maximum ripple occurs when theta equal to 90 degree. That is something like which you can see over here actually. And as the omega t varies, different value of omega t, like 0 to 90 degree we have taken omega t, and we found that normal operating conditions at theta equal to 90 degree, the ripple is maximum for 1.8 millihenry. Now let us see that if current equal to 60 degree, 60 ampere, now if current equal to 0 means ripple is close to 0, there is no ripple, and all theta is remains same also. Now if inductance is made half of the earlier one and current is maximum, then again we found that the theta is 90 degree is the place where maximum ripple comes actually, and it is same for current equal to 0 also. And when inductance is made double, then also the results is same actually. So it gives a understanding that here actually voltage is reduced, then also the results remain same actually. So one conclusion which you can derive from here is that theta equal to 90 degree is the place where you can get the maximum ripple, and that occurs when rated current is maximum actually. So whether this point can be substituted back in this relation to get some simplified solutions are possible or not. So we substituting this theta equal to 90 degree, then we found that the ripple differential, first order differential for the ripple, we can equate to 0. Then we can get two solutions, like the ripple can be maximum at theta equal to 90 degree, or it can be at VDC by 2V. So two solutions can be obtained. So we can do the second derivative also to find out that which can be the viable solutions. So we found that in that case, again two solutions can come. Like when you're having a 2V by VDC less than 1, that is one solution. Like, VDC can be greater than 2V, there will be a solution, and if VDC is less than 2V, there is a solution actually. So you can substitute sin omega t equal to VDC by 2V, and you can find out relation, like, relation for ripple, you can find it over here. So in summary, actually, you can get the maximum ripple occurs at theta equal to 90 degree, and if your DC voltage is greater than 2V, there will be a solution at omega t equal to 90 degree. If DC voltage is less than 2V, there is a solution at a sine inverse VDC by 2V. So it means that the maximum ripple, even it is occurs at power factor to 90 degree, the place where it is occurring, that depends upon the DC voltage. So this insight is something like which you can get analytically only. Like if you have a simulation results or something like this, understanding will be pretty difficult actually. So analytical from analysis, you can easily gives a feel that where can be the maximum ripple possible and how or what are the parameters to which it is dependent. So in practically, generally VDC will be less than 2 times V, where V is the grid voltage. So since VDC is less than 2V, we can see that the maximum ripple can be occurred at a point where sine inverse of VDC by 2V is applicable. So you can substitute these values and finally you can get a relation of peak to peak ripple is nothing but VDC divided by 8 times L into Fs into 1 plus omega LV divided by V. So you can simplify over the and you can find out the inductance value actually. So this simplified equation you can use it for the to derive the inductance value for the given ripple, peak to peak ripple, DC voltage, as well as the frequency and the grid voltage and the operating current applications. So so then next thing is basically generally if since this is a grid connected system, you may not be required a AC capacitance in the output side, but if it is a inverter system, then probably you may require a AC capacitor so to make it a sinusoidal voltage appearing at the output side. So in that condition, how this AC capacitor can be so if you see over here the output side, it becomes an LC circuit. Like it's a second order system, it becomes a second order system in picture actually. So so to solve this one of the method we can do basically, like when you have a larger ripple, you can put a capacitor to reduce the larger ripple to the capacitor, and output voltage can be made sinusoidal. So but the second order system designing is pretty difficult actually in that condition actually, because if you are not properly designed, it can give you ringing, more ringing will be there, and it can be dance to a oscillatory nature actually. So so effective switching frequency, now it becomes equivalent circuit can be drawn for 2 times Fs because you are operating in a unipolar modulation. So the effective switching frequency you can choose as 2 times Fs, and the transfer function of the LC circuit you can derive it. So from the transfer function, actually you can draw a magnitude plot which is for the above transfer function you can give it. So it gives decay with minus 40 per decay because it's a second order system. And and you can choose omega, like operating frequency omega is something like 10 times omega c. Like on frequency, if it is 10 times omega c, you can choose 1/10 of that as an operating frequency, and you can find out resonant frequency you can choose just 10 times omega c, and from that you can find out what is L and C requirement is there. So there will be a relation which is connected to L and C in the relation, you will get it. L anyway you already derived with the ripple conditions, and from that you can derive C, you can derive it. Now comes apart from this selection, now instead of going through more on controllers, we have a slight look on the device and other components which comes as a part of inverters as well as for part of the DC-DC converter also. Now in most of the applications, probably if it is a larger power, we may be using IGBTs. If it is even based on the operating frequency also, like if the operating frequency is something around maybe 10 to 30 kilohertz, probably IGBT will be a suitable solution, and otherwise we will go to MOSFET also. So a typical understanding will gives for the IGBT. Like whenever we are choosing an IGBT, generally the selection criteria will be such that the voltage rating of IGBT preferably will be operating at 0.6 to 0.7 times the maximum operating voltage of the IGBTs, and the current can be, we can choose it something around 0.7 to 0.8 times the rated current. The reason is basically when you consider any devices like IGBT or MOSFET or any semiconductor devices, there can be a voltage stress as well as thermal stress will be there. Now when you have a overcurrent, it will lead to a thermal stress. When you have an over voltage, there will be a dielectric breakdown will be there in the semiconductor. So but the dielectric breakdown is something like a very quick in nature. Like when you have a slightly larger voltage, immediately it will break down. But thermal is basically a slow process actually. So in that condition, probably you can stress the current slightly larger, but voltage is better to limit within a suitable range itself. Now the switching time, again you have to choose the device such that the switching time is within your requirement. Like for example, if you are operating switching frequency something around, assume that 10 microsecond is your switching period. Now in 10 microsecond, if your turn on and turn off conceals something around 2.5 microsecond, it means that that switch may not be able to use it for this particular application. So at least you consider that your turn on and turn off time is such a larger value, such that you are getting almost a square wave in nature you are getting. Now to identify the thermal design for the IGBTs, there are many characteristics they are providing. One is the energy curve they are providing in the data sheet, like a turn on energy curve will be there, turn off energy curve, then recovery energy curve will be there. Then as well as junction to case thermal resistance is another parameter which is important when you are choosing an IGBT or devices in your applications. So when you are selecting a device, main thing which you have to understand is basically how from the data sheets or whether the device operating conditions, operating voltage as well as operating current are within the requirement or within the specifications what you are intending. That is something like which you have to look on, and as well as you see that a proper data is provided to estimate the losses in the devices, and also whether the required gate drive conditions they are provided. All those things you have to look on. We will have a data sheet and we'll just go through the data sheet and see that what are the parameters are important when we do a selection for the devices. So this is a typical curve which is shown over here for the case of an IGBT. So generally they will give 4 curves. One will be related to the right hand side top. If you are doing is basically a saturation voltage characteristics versus the collector current. So here actually you can find out the conduction loss in the devices using the VC versus IC characteristics. And in the bottom actually you have 3 curves. One is on the left hand side is basically again it is a forward characteristic, that's of the diodes, where you have a collector voltage as well as the current will be there. So from that you can find out the loss in the devices. And the center one it is nothing but the switching losses. So they are giving the E on and E off curve, like when devices are turning on, how much energy is loss is there, devices are turning off, how much energy loss is there. So those curves will be provided in the data sheets. So from that you can estimate the switching losses in the devices. And the right hand side is basically reverse recovery loss in the diode. That also you can that curve also we are providing to find out the reverse recovery loss in the diodes when it is turning off. So in summary, when you look on this particular curve, one thing which will be very clear actually, in all the curve there will be an operating condition they are provided. Now these operating conditions may not be your operating condition. So like by choosing this particular curve, you should be very cautious that whether this operating conditions is matching with your operating conditions. If it is not matching, you have to extrapolate or you have to get a new curve from the supplier, or you have to find out a methodology how you can port this curve to your requirement. So as I mentioned, different curves they are giving, like conduction loss will be providing, and E on and E off loss will be providing, and there are many tools which even the manufacturers are also giving, like there are software called Microsim from the Mitsubishi, or it can be from Semicron or Infineon. There are different software they are providing to compute this losses in the system. But in all cases, one thing which need to be clear that all these computations are based on a typical nature of the curve, actually, the nature of the current or nature of the voltage. If your system is not falling into the particular nature of the voltage and current, then again using this particular software, you will be landed into a erroneous result. So it may be better again that in your circuits you can import the curve and you can compute how much losses are coming. Like, you can with a device you can choose it, and device you can characterize it in the simulations with either you can directly get the device from the supplier, or you can even port the data sheets into the device and characterize the devices to get the losses appropriately. So when the devices are ready, then next comes the heatsink and fan. So heatsink and fan is again a typical trivial system actually for the designer, because the heatsink, fan and the device, these three things you cannot design independently. Like you choose a heatsink first, then you choose a fan, then you choose a devices. That type of design will be always become may not be an optimal solution. The reason is basically when you take a fan and a heatsink and you connect it together, like when a fan is simply lying in or in an open space, it will deliver some air actually. But when it comes in contact with the heatsink, there will be an obstruction. So the air fan velocity will get changed, and the operating condition of air fan combination, that also will mean the fan and the heatsink combination, that will be getting disturbed, or that will be different actually. Now the heatsink, when the device comes on the heatsink, then as the device is getting or working, there will be a loss generated in the devices, and heat transfer will be there from the devices to the heatsink. Now this heat transfer again, if you are considering, like assume you are taking a heatsink of something around maybe some 1 feet by 1 feet, and if your device is very small, tiny on the top of that, then whatever heat is generating by the device, that cannot be spread out throughout the heatsink, because heatsink is very large and your device is very small. So whenever you are choosing a heatsink, you have to be clear that what is the dimension of the devices, and whether your maximum, at least 70% of the heatsink is utilized properly by the devices. Otherwise, there is something called as spreading resistances that will come in play, and your you will not get whatever result you are expecting with the heatsinks actually. So in generally, what we do basically, when you are choosing a heatsink, the temperature of the heatsink will try to keep it 75 degree, or sometimes may go to maybe 80 or 85 degree also. But while keeping the 75 degree, you have to ensure, whatever degree, whether it is 75 degree or 85 degree, you have to ensure that the junction temperature of the device should not cross to the value which is mentioned in the data sheets. So a typical estimation methodology is shown over here. Like there can be an IGBT or diode will be there. There will be a loss generated by the IGBT will be, as well as loss generated by the diode also happening here. And there will be a thermal resistance. Thermal resistance is basically an indication of the rise in temperature it shows. So it will be given in the data sheets. Thermal resistance of the IGBT as well as thermal resistance of the diode also given in the data sheets. So as the power goes through the resistance, there will be an increase in temperature, or there is a drop in temperature can happen. So from the junction, there will be a drop will be there to the case. I think it will be putting it the other way around. Like the case temperature will be increasing as the power goes through the RTH of the IGBT as well as the diode to reach a higher value at the junction. Now these two power will come together, and in the case point, it will come together and flow through the case to sink area. So there will be another thermal resistance will be given by the manufacturer for the case to sink, and from the case to sink it goes to the heat sink and to the ambient will be there. So from heat sink there will be another thermal resistance. So this network, this resistance network can be used to find out the junction temperature for the devices if when you are selecting a heat sink. So the heat sink here actually when the device is selected, then RTH of the devices diode will and the case to sink will be fixed. Now the heat sink resistance is something like which you have to choose properly, so that the junction temperature is not crossing the limit. Now, as I mentioned, the heatsink fan also is again a trivial selection procedure. So as I mentioned, when a fan is connected to the heat sink, there can be a pressure drop will be there, or an opposite and back pressure will be applied on the fan, and that will reduce the airflow actually. And similarly, in the heat sink also, and when air is flowing through the heat sink, again there will be a back pressure on the airflow, and again whatever air we are expecting through the heat sink fins, that may not be happening actually. So the heat sink, there will be a pressure drop in the heat sink, like when there is a pressure versus air velocity curve provided by the manufacturer of the heat sink will be there, and as well as for the heat sink there will be a thermal resistance versus air velocity also provided there. So in generally, whenever a heat sink, when you are looking at, two curves will be important. One curve will be heat sink pressure drop curve, second one is heat sink thermal resistance curve. So the right hand side figure shows the thermal resistance versus air velocity. So as the velocity is increasing, you can see that thermal resistance is reducing. Thermal resistance is basically the amount of temperature, increase in temperature. But you can see that after a certain increase in the air velocity, the amount of reduction in the thermal resistance is very minimal actually. So if you are putting a very big fan in the heat sink, don't expect that there will be a larger cooling can come, because as the air is largely increasing, there will be turbulence inside the fans, inside the fins, and which will not give much gain on that actually. It's a reduction in the thermal resistance, you can see it will be minimal actually. Now the second curve which I mentioned is basically heat sink pressure drop curve, which is given on the right hand side, where you can see that as the air velocity is increasing, the pressure also it will be keep on increasing. Like the back pressure will be keep on increasing as the air velocity will be increasing. That is something like which is given here. Now the second thing is basically about the fan. When you are selecting the fan, again the fan manufacturer will give another curve called basically a pressure versus again there is a air velocity. But here actually something different, like as the pressure is increasing, pressure on the fan is increasing, air velocity will be reducing actually. So when you compare this curve with the heat sink curve, one is going upward, other one is going downward. So in that condition, you can just connect it together, these two things, or put into the same scale. Like the heat sink, when you're considering the pressure versus air velocity curve will be going upward, and for the fan it will be downward. So there will be a meeting point. That meeting point will be your actual operating point, and that will be the actual air delivered through the heat sink. And using that air velocity, whatever you are getting through the meeting point, that air velocity you have to use it in the thermal resistance versus air curve, so that you can find out what is the actual thermal resistance for the heat sink which you are using, because it is dependent upon the air velocity, of the fan actually. So in that context, the selection of the heat sink as well as the fan will be come together rather than going into the separate entity actually. So that's again an involved work actually, because you have to find out the velocity curve for the heat sink, then for the fan, then you have to connect it together and find the operating condition, then put it into the again back to the heat sink to find out the RTH, and that RTH you have to use it for the selection of RTH. You have to use it for identifying what's the maximum junction temperature can be happen in the semiconductor devices. Now come to the another component which is involved in the design of the inverter or any DC-DC converter also is basically the gate driver circuit. Now gate driver circuit in generally does many activity. One is basically provide an isolation, then it provide a unipolar to bipolar signal. Then again this amplifies, like you may be giving a low signal from your controller and it amplifies to a high signal as it reaches to the gate point. Then also it gives a protection also. So so in summary actually, generally when you see a gate driver circuits, the gate driver circuits input supply may be a 15 volt, so there will be a DC-DC converter again inside the gate driver circuit which converts this 15 volt to plus or minus 15 volt to deliver to the IGBT. And if it is a MOSFET, it can be from 0 to 15 volt as it works. Now here actually when you look on when designing or selecting the gate driver circuit, there are two phenomena which we can consider, like whatever gate charge required for the devices for its operation, that will be provided in the data sheets. So a typical gate charge characteristic which is given in the data sheets of the IGBT is given in the right hand side. where you can see that if you are operating from 0 to 15 volt, the maximum charge required is basically 2700 nanocoulomb. That is required for the devices. Now assume that if you are switching the device to the negative also, then you have to extrapolate the curve to the negative minus 15, and that requires again 750 nanocoulomb. So what is the maximum nanocoulomb requirement for the IGBT to turn on? That you have to calculate from the gate charge characteristics, and the gate driver manufacturer will provide what can be the maximum that can give it, and whether it is matching, then that gate driver can be used for this particular application that you can consider. So as I mentioned, there are again many gate driver circuits are available in the market also, and a typical is shown in the particular figure. Yeah, in summary, this whatever design aspects is there, all things I did mention. With the lack of time, more I thought maybe I'll cover into the hardware aspects rather than into the equations in this conditions. So here actually we'll just work out some of the point, like for example a device when you're considering. As I mentioned, the device, this is a typical device which is considered over here, is from UPEC actually. And where you can see that when you are looking at the data sheets, some of the important points you have to consider. One is basically what is the collector emitter voltage maximum allowable, and here it is given 1200 volts. Then continuous DC current rating. So continuous DC current rating again becomes very important. You have to see that what is the operating conditions at which it is mentioned. Like when you see it is at 25 degree, it is given at 100 ampere, but at 65 degree it's only 75 ampere. So again you have to see that if you are using this particular devices in your applications, what can be the maximum temperature possible. If it is 65 degree, okay, you can use it up to 75 degree, 75 ampere. But if it is going more than that, then again it is a question actually. So you have to understand that whether your devices will work in that condition or not. So, but this current rating is mainly concerned about your thermal aspects. So probably you can ensure that whether your temperature is not going beyond your junction temperature. So in this particular case, the maximum junction temperature probably they mentioned in the data sheet something around 150 degrees Celsius. So we'll look on where it is given actually. And similarly, they also given the gate charge. This is something like which I mentioned. There will be a gate charge which is given over here. So maximum 0.8 microcoulomb they mentioned. And this goes from minus 15 to plus 15 voltage. And similarly, some other aspects which you can see as you scroll down, especially the curve and other things. Probably you can work out as in the next sheets. Yeah, so here actually another important thing, as I mentioned, the thermal resistance system. So we'll just find out where is the thermal resistance curve is given actually. So probably, yeah, here actually it is provided. So you can, yeah, for that probably stop on this. Yeah, here actually they are given the thermal resistance, junction to case thermal resistance they are given. So RTH junction to case, and this also per IGBT they are given. And similarly they will give for the diodes also, they might be given in the data sheets. And short circuit data is another very important thing which we have to consider, because whenever you are operating this particular devices in your system, when short circuit comes, what can be the maximum current handling capability of this devices, that is something like which is very important aspects. So there are some important points which we should not miss when we are going to the data sheets. And again the curve is also very important, like along with the table gives a typical case only, but curve gives a larger spread of the conditions. So all those things probably we have to see. So these are the few curves where we are mentioning about energy curve, which is somewhere is given over here. Like this is basically an energy curve for switching losses for the diodes as well as inverters. So this is the recovery charges the right hand side. So these things probably becomes very important when you are looking on this one. And similarly, another one more thing, we'll just go through that. This is a typical data sheets for the heat sink, where you can see, as I mentioned, you can see this particular curve like RTH, thermal resistance versus air velocity. Then as well as they might have given pressure versus air velocity curve. So a similar data sheets you can find out for a fan also, there also probably they will be given this typical data sheets for the this pressure curve they will be provided in that condition actually. And another thing, this is a gate driver. Again, a gate driver is also very important. And probably you can see this voltage level for the gate driver. You can see over here, and what is the maximum output current it can deliver. That's also provided over here. And again, as I mentioned, what is the minimum gate resistance requirement that is required for this connection. That also they provided a maximum operating frequency. That is another parameter of important. So when we look on the data sheets, these things are very important and match with your requirement, whether it is matches with your operating condition. So that is something like which is secondary. And probably this is the maximum rating for the output charge per pulse, which is around 2.5 microcoulomb. That is maximum you can deliver it. So if your device demands more than that, then probably this driver card cannot be used for such an applications. Yeah, then comes about the capacitor. So as we have seen, this again an essential part of the system actually. But when we look on the capacitor, there are many things to be considered, like the ripple current. When we look on ripple current, generally they will mention ripple current at 100 Hz only at 85 degrees Celsius. But we have to see that along with the frequency, the ripple current varies. So there will be given a table over here where you can see that how much we have to multiply with the ripple factor with the corresponding to the frequency that we have to consider, and with the temperature, what can be the multiplication factor that also we have to consider to get the actual ripple current which it can carry actually. So and yeah, so again they will give that ripple current at 100 Hz will be provided for different value of the voltage as well as the current. And along with that, they also will be providing some of the mounting instructions, how you can mount it, like what are the placement and other things, how this safety event should be there, whether it should be the down or up. So all those things to be considered when you are mounting the devices. So yeah, so that's more about the device packaging and other things. So one more thing, probably this is a snapper capacitor that again for the device switching, when devices are switching there can be a spike. So this again a capacitor selection. There also the frequency versus change in capacitance comes in picture, as well as the temperature versus dissipation factor, and different other curves also they are given in the picture actually. So and this is basically a type of a MLCC capacitor where you can have multi-layer things are coming to the plates. So in nutshell actually what we have seen basically in inverters how the inductor can be considered, because that is something like which is largely deviated from the DC converter things, and from that a typical case we have considered how the practically how you can choose the devices and what are the things to be considered and how you can select the capacitance devices and the heatsink selection, fan selection, and the gate drive selection. So these are the components generally fit into many of the, like even if they are DC converter or inverters, all these components are common, and but their role will be different and their requirement as well as the specification will be different. But you have to be properly choose these things for giving a reliable solutions to the system. Yeah, I think that's it for this work session also. We just wrap up. Thank you.
Thank you, Dr. Shubha. Yeah. So, looks like one question which we had received earlier was, what is the importance of an inverter in an electric vehicle? So, Dr. Subhash, maybe you can answer this question.
Yeah. Yeah. So when you see, mainly when you look on the electric vehicle, the main point is basically, the charging aspects. When you see a charging aspects. So here actually there are many charging methods are the which people are talking about. There is a fast charging, then there is a slow charging, and then there is AC charging, DC charging. There are many methods people are trying out, because how you can reduce the time and how you can quickly charge the battery. These are the concepts which people are talking about. So anyway, when you look on the inverters always plays a role in these aspects, because the source of energy is basically from the AC actually. So until we didn't shift complete to a DC transfer system, so you have an AC transfer system. So then two-way it can play a role. There is an AC it's coming, then you have a conversion to DC is required. So there is a AC to DC conversion required. Probably that is something like where an inverse of inverter comes, like we can put a converter actually in place of the pole actually. And these all things will come in that picture actually. Then putting the other way around, there is a vehicle to grid concept where you can connect the vehicle to the grid. So there actually again the battery from the vehicle will connect to the grid again through the inverter applications. So inverter will play a role in electric vehicle either to the charging of the battery or from the battery to the grid connectivity. So that is so these are the places where it may play. But inside the vehicle, probably it's become a DC system, so maybe some subsystems will be there, like a polling aspects, all those things is required, where again we may require a DC system, then will play probably. But generally, most of the cases are DC-DC converters in the inside the vehicles rather than inverters. Yeah, I think that's it.
Yeah. And to add to Dr. Subhash's answer, mainly you will also use inverters because your motors in the vehicle will be AC powered. For example, PMS machines or AC machines. So this is also one reason why you would need to have an inverter. And Dr. Subhash, now I would like to say thank you very much for this session. I think it is very rare that students get such a detailed explanation on how you would go about choosing components, and which is very different from what you would see in a normal textbook. You have also talked about how you would choose components from by reading a data sheet. Also, I hope the students are able to grasp this methodology at least. I know it is difficult for all of you to understand all these factors in such a short time of 1 hour. But the point of this session is to more or less understand the methodology or the thinking process that you should have to meet the problem statement of design and control of an inverter for an electric vehicle, right? So I hope that I know for sure that the methodology has really been passed on really well, and so thank you for that, Dr. Subhash. Thank you so much for joining us and being a panelist on today's session.
Thank you very much.
So now we will have a 10-minute break before we move on to our next session. So everyone, maybe you can go grab a cup of coffee. Okay, maybe it's a bit too early for coffee. Okay, actually, no, it's never too early for coffee. So you can go ahead and grab a cup of coffee and be right back in 10 minutes.
Arun, hi.
Hello. Hi,
Hi,
Praveen.
hi.
So, shall we start?
Yeah, it looks like yes, we can start now.
Okay. So, hello everyone. So, hope everyone is having a good time. So, next I invite Mr. Shivam Ingle, who's currently working as e-powertrain engineer in Blueberry's lab, Bangalore, and has a vast experience working in different aspects of EV, from development of powertrain to system testing and validation. So without further ado, I welcome Mr. Shubham Ingle, who will be taking presentation on smart grid. Sorry, on design and control of onboard chargers. So welcome, Shubham. Here. Hi, Shubham. You're on mute.
Oh, thank you, actually. Are you able to hear me, guys?
Yeah. You're audible.
Yeah, actually, thank you for inviting me for this beautiful session, actually. Uh, so, before starting this session, I just want to introduce myself. Actually, my name is Shubham, and now I am working in the McLaren UK. Right now, I'm in the UK actually, and through the Blue Binary, because it is a supplier actually, and McLaren is a client for us. Before that, I was working in the Vietnam for the WinFast, and yeah, we developed some premium vehicles there. And before that, I was working in the CNHI. It is also a UK based client. So okay, so are you able to see my screen?
Yes, it's visible. Yeah.
Oh, okay. Thank you. So, just before starting the session, actually, I want to highlight, because I was there in the session and I heard that someone asked what is the inverter actually. Very basic question. So, I just want to remind him, if he saw the Three Idiot movie, and where the principal will ask the Raju that how the induction motor works. So there, what the best play of the inverter will come. So in the EV, actually in the electric vehicle, so when you want to power the induction motor, you do need a inverter actually, unless if it is not a DC motor. So that is the basic thing. And now the second thing which just want to ask before starting this, because this all session we are just playing with the AC to DC, DC to AC, and DC to DC. So I just want to ask a simple question to attendee. What is the requirement of DC to DC in the vehicle? Just a simple question. So I will start my session further. Hello. Hello. Am I audible to everyone?
Yeah,
Yes,
Shubham, you're
Shubham.
audible.
Yeah. You can continue. Yeah.
Okay. Then I will continue. You can just put the answer in the chat. No problem. So, okay. So the agenda is actually from I want to cover actually the onboard charger, but I will start with the high voltage training. It is just a small slide where you will just get to know that if you want to enter in the EV industry, that it should be mandatory, and if you are working on the high voltage system, that is also mandatory. So the safety first, so we will cover that first actually. Second thing, actually the overview of the DC charging, because I want to cover the onboard charger, which is actually required for the AC charging, not for the DC charging. So I just want to make a difference of DC and plus AC, so you will get a more clarity, okay, why it is really needed of the onboard charger. Then I will discuss the type of charger which is available, then the AC charger available in the market, and then I will explain the functional block diagram and the signal interface with respect to how you can put an approach while designing the onboard charger. Then I will explain the charger interfaces and the standardization. I mean, what standard you should use, what standard you should refer while doing this all the activity throughout your development, because developing something is quite easy, but it should match the standard. That is more important, because most of the people who develop the onboard charger or any of the EV market, when they go for the certification, they get fail actually, just because they don't follow the standardization. So it is that much important to this. So my first Okay, so my first slide is actually the high voltage training, which actually in the Europe country, even it is given for the sanitization worker also, because if any accident is happening on the vehicle, so if someone is going and just helping other, so he should know that he should not touch the high voltage wire, because the voltage will be above 400 and the most of the vehicles. So that is there. Then you have the level 2 certification, which is there for the people like us actually, to get all the theoretical aspect, to understand the capacitor, to understand the capacitor voltage, to understand the capacitor discharge, because even though when your vehicle is not powering, but still there is a chance your capacitor is there, that okay, it is fully charged, and if someone is accidentally touching it, then it will be like sudden death. I mean, that can be that much dangerous. So that all the theoretical aspect will be covered in the level 2, and in the level 3 you will have the hands-on experience on the vehicle itself, and you will charge and discharge the vehicle. You will remove the component, you will handle the HVL, you will handle all the safety measures. So that is there. This actually I am level 3 certified in the this one, which is actually provided by the TUSU Germany. So that is required. So just to tell you, actually this is important, just you are aware. Then I will start with the overview of the DC charging actually, but the thing is, it is not a part of onboard charger, but to see the difference, because I am having a next slide, which is actually sorry. So next slide is actually the AC charging. So in the DC charging, so actually you will have, if you okay, if you see here, actually this is the EVAC, where you have the entire your charging unit, and then you just have to plug in your vehicle, and then your BMS will just handshake with the EVAC, and then you will start the charging. So if you see here, the high level communication is required. So look at, for every line I have added one standard. For safety measures required, yes, the standard is there. High on time, and this is actually just a highlighted point, because for the EVAC you need a one-time investment cost, because it's a big setup. And then the charging power is capable due to missing space and the vent constraint. Yeah, and typical charging power is actually greater than 50 kilowatt. And in the later side, you will understand why it is 50 kilowatt and what are the chargers which is available in the market and which is actually above 50 kilowatt. So now I will just move to the second slide, and other things I will cover just to give the overview. But if you see in the picture, you are not seeing any OBC small block or any OBC mentioned here, because this is purely DC charging where you don't need onboard charger. Okay, so now from here I will just start giving the proper understanding of the OBC, how it will work, and how it is connecting with your BMS, how the handshaking is going on, everything. So if you see, again the standard is already mentioned, because whatever you do, it is all you have to follow the standard and you have to start developing. So low cost, high availability, yeah, sure, because we do have the power supply available at our home only. Yeah, it is low cost because you don't need any big setup or something, because the OBC on board charger is already there in the vehicle. So I think organizer have to give I think permission to people, but I have many questions to ask. But better I will ask the question and I will myself will give the answer. So the basic question, why we need a OBC? So in the previous slide, the OBC was not there. Why? Because our battery is a DC source, correct? And then you have a direct DC source from the EVSC. But in our case, if you see in the Tesla also, you can get the 1.5 kilowatt charger or 3.5 kilowatt charger, where you can just plug in your household. I mean, you can plug in your home and then you can charge the battery. But how is it possible? So there, what the OBC will play a very important role. It is on-board charger. So, but we have already studied this in the college. Onboard charger is nothing but you are taking the AC source, you are converting to the DC. So it is nothing but AC to DC converter. And that actually we have designed, I think in the third year itself, we have the practical to design the AC to DC converter, where you will take the transformer, where you will take the resistor, you will take the capacitor and you will design on the PCB or the breadboard. I mean, that was a good activity. So if anyone have done that, it is nothing that only with little big picture. I mean, then you will use the big capacitor, you will use the big transformer, and like that. I mean, it is just that simple. But when it is coming to the EV, then you have to play safety measures. You have to make sure the communication will be proper. You have to make sure the kilowatt rating, that the efficiency of the OBC, it should be high. So that you just have to make sure. So if you see, rectifier is exclusively used for one single EV and add extra weight to the vehicle. Definitely it will add the extra weight in the vehicle if you want to give the OBC, because that OBC unit will come and it will add the extra weight in the EV. And we as a EV enthusiastic, actually we are struggling to reduce the weight of the EV car, because the thing is the battery is already too big, and if you are putting one more onboard charger on that, and the weight will be more actually, it will do impact our range means how much kilometer it will go. Then the low charging power, typically 3 to 22 kilowatt, due to space, weight and cost limitation. Low level communication is used for the status provision. I will explain this, what is the low level communication is used, how the status provision, why we need a status, everything I will explain in the next slide. Then a bigger challenge, the regional difference in the low voltage grid, like amplitude, frequency and quality. The thing is, actually, if you see in the right hand side, this CCS AC type 1, so if you see the flag, it is actually the USA. And then if you see the CCS AC type 2, which is there used in the rest of the world actually. So the thing is, now I am asking the question and I will myself will answer. CCS AC type 1, okay, so if the model is a US variant means it is completely designed for the American market. So if the CCS AC Type 1 is there, okay, and if I'm bringing that vehicle to India, okay, and then I'm plugging from my home, my household supply to that vehicle, is it that going to work? No. Why? The simple question. Why? They said frequency. So frequency is there will be the 60, in hour it is 50. The voltage will be 120 and 240, hour is 240. So you just have to make sure that okay, everything will be fine. So this is the reason actually when we say the CCS AC Type 1, then that will come for the US variant. Then CCS Type 2, which is actually they are used in the rest of the world. So Vietnam also count, that time I work on this. And then GB by T in the China always will play the always different than others. So this is the main role. OBC, you just have to fix the OBC is like, just you have to take the AC and convert it. This it is AC to DC converter, nothing else. I mean, there is no rocket science in this. Now the second slide which I want to explain you, because when you are doing the working on the onboard charger, but the basics should be clear. Like, okay, so if I am working on the onboard charger, okay, so these are the AC gun, so these are the DC guns. So if you see the type 1 is there, if you see Japan, okay, so now this one is there, and then we have the type 1 then for the America. Then while seeing the gun, you also should tell, okay, these are the AC gun. In the AC gun, now the onboard charger will play the role. Now in the DC, it will not play the role, because BMS is there to handle nothing, because it is just a direct supply to charge the battery. Then if you see type 2, which is for the Europe and the rest of the world, and then the China, it is actually the GB by T is used. But if you see actually this is CCS, which is actually the combined charging system, is actually combination of this AC and plus DC. You can see here, this one is AC, the top one, and if you see this DC plus and DC minus, actually this is DC plus, DC minus. This too big, you are saying this is DC plus, DC minus. Other will be used for the actually for the AC charging. So now actually how that gun will look like, I will show you in the next. So this is the gun actually, the various adapter available for contacting any EV actually. So if you see, I already told you CCS, now AC type 1, CCS protocol AC type 1, CCS type 2 charger. Then we have GB by T, I already told whether China will use. So now, but if you see on the other hand side, this one right hand side, which is actually CCS DC type 1, but if you check, it is the combination actually where AC and DC. So this is how the gun will look like. Just forget about this end, actually this will go to one simulator, that's why it is came, but it can be our household pin, which is 3 pin actually, just a 3 pin. Here also you will have 3 pin here also. Now the next slide, which actually I will tell where I myself use this all the charger in the whoever actually whatever vehicles I actually work on. I work on many models which is actually pure EV from India to now I'm working on the hybrid vehicle. So we do have a charger. So charger available in the market type 2, 1.5 kilowatt. Yeah, 1.5 kilowatt. Then we have 3.5 kilowatt, 7.5 kilowatt. Yeah, AC, 11 kilowatt AC, 22 kilowatt AC. So if you see in the first slide itself, I already mentioned the limitation there. And then we have the 30 kilowatt, which will be a DC in the type 2. Then we have the 60 kilowatt, then 80 kilowatt, then we have the 50 kilowatt. 50, actually the 250 kilowatt is actually also called as 250 and more than that, which is actually used to tell, like people used to do the marketing, like the super fast charging, the fast charging, like they will use the term SFC, like the super fast charging. So nothing else, it is just with the more power. But doing the super fast charging will do have the limitation. I mean, it cannot be do more frequently because it will impact your battery pack. Then my next question is actually, suppose you have designed the OBC which is having the rating of 10 kilowatt, and then if you are plugging the 22 kilowatt charging gun, is it going to work? So the answer is actually yes, it will do work, but with the limitation of the 10 kilowatt, because in the most of the vehicle OBC will set the limitation. I mean, you will not having like with the more kilowatt, it will be less, actually 10 kilowatt or 11 kilowatt, and then someone will go with a little higher range. And then on the other hand side, which is actually the type 1, because I'm playing, because these two chargers actually use in all over the world, so that's why I'm focusing on this two only, because the GB by T and other CHAdeMO, which is very restricted to the specific countries actually. So if you see the type 1, I do have 1.5 kilowatt. That is actually the home AC. Then we have the 3.5 kilowatt, which is actually also home AC. Okay, but when it is coming to 7.5 kilowatt, then you need a little small unit actually, where you will have the controller and other thing to just for the safety and giving this much power to the vehicle. I mentioned home AC. So this is actually your just a plug-in to your household supply. Just plug in and just put the car in the parking and just start charging. But this is come up with the unit. I mean, if you see here, this is actually for the DC, but a little small unit. I mean, just a size of your college bag. It will come like that. This 7.5 kilowatt, this 11 kilowatt, it will come like that. So in the right hand side, actually, if you see this ABB, which is 250 kilowatt DC fast charging, which I told SFC, and then we do have the 60 kilowatt CCS2 charging. And the only thing I forgot to mention here, actually, if you go to the 30 kilowatt, it will take the respective time. Okay, so then if you go with the 60 kilowatt, it will take respect. So 60 kilowatt, actually, when we have a battery pack of 400 volt, actually it will take around 1 hour. 1 hour it will get, depend upon your actually the C rate, but it will get charged. Then 80 kilowatt, but with the 250 kilowatt superfast charger, it will be in just 30 minutes, very quick. I mean, less than 30 minutes actually. I told more. So then, but why I'm mixing AC and DC, to just clarify the difference. Otherwise, it will be a little difficult. Then, sorry. Okay, then now I will cover this is the functional block signal interfaces, because I was there for in that DC-DC session was going on. I was there where they have covered many actually the in-depth, actually it was very in-depth. It is good actually, but I will cover little at the top, because you people now it is you are in 4th year or 3rd year. We already in the 2nd year or 3rd year, we already designed the AC to DC, so we know what are the components are required there and how to choose that. You know that actually already, how to take the capacitor, how to take the resistor, depend on the rating, so that you already done. So I will tell on the actually with the industrial perspective, how you will design the DC-DC when you will sit and when you will take the pen and paper, how you will start designing. So imagine you having a group of 4 people. So now if you see, I have these are the functional where the BMS will play the role. Then we have this vehicle control unit. You just call it as it is a master unit in the any of the vehicle. So someone will call MCU like master control unit or a vehicle control unit. So just to make sure it will be just like the big unit will be master for everything. So So now in the vehicle control unit, so this is our one of the controller. You can take any of the controller which is available in the, like you can take Delfino is there, then ARM Cortex is there, then which one is Raspberry Pi is there. You can just design the first, you just draw on the paper and then you can just design and start doing the coding for it. It will be easily available on the internet also. I mean, no need to do it, but you just have to make sure that you are using everything properly and you are understanding all the prospects. So now I am starting designing with you. Actually, now everybody is sitting now and just we are starting. We will develop the block diagram first. Okay, so we design the block diagram. Okay, I need one OBC, so this will be just a simple our AC to DC, which we design in the third year or fourth year, as simple. So this is design. Okay, this is design, or you can just take it from the market, or you can design yourself. It is also easy because I also did it. So then we have the vehicle control unit. In that I have highlighted three functions, which is actually the AC charging. Then I am having the function 2, which will be like someone from your team is working, so it will be like heating and cooling, because when you are doing the charging, you have to just make sure that your onboard charger is not getting hit. Okay, then the second is actually your onboard charger controller. Why vehicle control unit will even control your BMS and then your OBC onboard charger. So one master is required. Okay, so in the vehicle controller I define function 1, which will be the AC charging. So how the charging will happen, how the handshaking with the OBC will happen. Okay, second, which is I am having the heating and cooling. Why heating and cooling both I mentioned? If in heating, if you are in the UK where the temperature will be go even below 0, so heating will be required. And cooling, if you go any of the other country, then cooling definitely if your OBC is getting heated. Then onboard charger control. But why this controlling part I didn't put it into OBC? Because I want to reduce the dependency of the OBC. OBC, I just want to work as just a slave. In the first line itself, I mentioned that the low communication. I don't want to put more hardware, more cost in the OBC. I will put in the vehicle control unit only. So first function, okay, someone is designing from your team. So like you can, like 4 people are there. So one is working on the AC charging. So he will take care of all the AC perspective. He will check all the AC things. Then someone is working on the heating and cooling. He will check all the heating and cooling related things. Then someone who is good in the programming, he will handle the OBC control. OBC control, how the controller you have to control actually. Now I started designing. Now I need a parameters. So look, doing the programming and doing the PCB designing, it will quite I can say little easy because everything is available in the market today. But defining on the paper, 2 minutes guys. Sorry. So defining on the paper, which is we call as a designing, where actually the architecture people will play the role more, and I am actually working in the architecture team only, where you will design first and then you will start developing. So how you will design? The first thing, now you want to start the communication between the OBC and the vehicle control unit. So you just have to define, okay, enable OBC. Very simple. Just start and on. So who will enable? Vehicle control unit will be enable the OBC. OBC don't have that much power. Even all the control will be the vehicle control unit, just because of the safety concerns. Now voltage OBC request. So vehicle control unit will request OBC, okay, this much voltage is required. Okay, now I think this got repeated, sorry. Then the current OBC requested, so which will be request by the vehicle control unit to the OBC, okay, this much current is required. to whom to need for the charging. To charge this much current is required, he will request to the OBC, look, this much I need, this much I need. And then to avoid the hazard situation, he will set the current limit. Who will set, look, these parameters are going from, if you see the arrow size, it is going from the OBC controller, the vehicle control unit to the OBC, but the logic is actually inside the vehicle control unit. It is not in the OBC, because that is our function 3 in the vehicle control unit someone is working. So 5 parameter fix. In this, I mean, more than this there is no parameter, because this is actually in the standard. If you check any of the vehicle, if you take any Tesla model, or if you take any of the BMW model, which is actually purely based on the EV, if you check, this many parameter will be there only. Then you now, someone who is working on the OBC, he will make sure that what the parameter should be go from OBC to the vehicle control unit. So from this parameter only you have to write a simple code. I mean, just to do the enable, you just have to define one digital out pin, which will be the digital into the OBC, just to on the things, and then supply will be already there to the OBC, and it will just the controller pin which is from the vehicle control unit. Now what are the things now you have to define from OBC to the vehicle control unit? So we will start from the first. If you ask the question to yourself only, okay, what should be there? Okay, so first it should give the status. So first it should just give the status of the OBC. Status means what? Is it OBC on? Is it OBC off? Because it is a feedback to the vehicle control unit, okay, that OBC is on, or the OBC is off, or OBC in the error state. So someone have to define this parameter. So I can say like how much state will be covered. One is on, one is off. Second is on a standby, I mean doing nothing, just standby. How we used to have standby in our laptops, similar kind of the standby. And then we have the error. Or is it in the error? It will give the health of the OBC also. Okay, it is in the error state. Then this is how you will design. I mean, every industry is following like this. I mean, just you have to design. Then voltage output DC. Again, I will ask the question, why we need 2 parameter here, voltage output DC and voltage input AC. Current input AC, why we need? Now if you see the simple thing, which is I already told, it is OBC is nothing but AC to DC converter. That's it. The only thing is actually how you are controlling from the master and how you are making it more safety, more safe, and I mean more. And other thing we can say the diagnostic is actually I told in the status OBC if it is in the error. So now the second is voltage output, voltage out DC. Yeah, voltage output. Why? Because the AC will come like from your household supply, which I explained to you, and then it will convert to the DC. So DC, now this is the controlling, but DC will go to whom? DC will go to the battery pack, okay, but not directly, because the BMS is there. Actually BMS will check, okay, whether the DC, if it is more than required, then it will throw the error. So DC is also there. This is how the functional safety work. I mean, I already told, developing is easy, but when you connect this all the dot now, then it will be more difficult. Okay, so because when someone is working on the OBC and he will set more DC output DC voltage, then the OBC guy will say, oh, this is not working fine. Then we have to, so I will come back to the OBC also, where it is BMS also, where it is having this many state actually. Okay, now voltage output DC, then current output DC, then your voltage in AC. So if you are in the India, so we know our AC voltage, then your current in to the AC. Okay, now why this parameter is there? Current max current output. So this is actually, you also have to set maximum this much only I can give, not more than this. We have to set the limit. And Why we are setting limit here and there? Because just for the safety concern. So okay, now one more parameter came. Look, AC charge temperature, because OBC will also tell to the vehicle control unit, look, this is my temperature. My temperature is 24, my temperature is 30, my temperature is 35. Okay, we set the limit of the 40. If above 40, then OBC will just disable. So who will disable? Not OBC itself. Vehicle control will send the command. How we will send? So this parameter is traveling from OBC to the vehicle control unit, and then if the threshold is getting hit, what vehicle control unit will do? It will just send the command enable DC. It will say disable OBC. Disable OBC. That simple. So this is how you have to design, you have to program. Okay, because AC to DC, you got someone from your team who is good in the hardware, he will design for you just quickly. Okay, he will take 2-3 days, he will design the AC to DC. Now someone from your team who is good in the programming and who is good in the thinking, you have to select all the parameter. So just imagine one thing, you have missed one parameter. Which one? AC charger temperature. One of from your guy, he missed the parameter. You design the OBC, you design the vehicle control unit. I mean, it is just a controller, but this one is small control than this with the specification and everything. So just one leaving one parameter, and if your OBC is getting hit, it will damage, and your vehicle control unit will not even know that. So you have to work like this. So that's what I said. AC/DC you will design. I'm damn confident, but you have to think about this parameter to make sure that there will be no hazard situation in your, there will be no failure, no technical failure in your project. And now we will go back to the BMS and vehicle control unit. So actually I will just give why this is actually the battery management system, which is there to monitor, to control everything, handshaking between the controller and BMS, and provide the suitable voltage supply to the battery pack. That is his job, and he will just make sure that your battery pack, your cells are okay. There is no cell failure, there is no the pack failure, or there is no short circuit in your battery pack. The BMS will monitor that completely. So now from your team, now the fourth guy who is working on the handshaking, because you just define the OBC, your picture is not over, because you have to make sure that that battery pack you are feeding through the OBC. That is also your job. It is not like you just design the OBC and okay, my job is done. You just have to make sure that the handshaking between the vehicle controller and the OBC is fine. Vehicle control unit and BMS is fine. Then BMS will give to the battery. So your ultimate aim is to just charge the battery, not just designing the OBC. So if you want to do that, then you also again have to define the parameter. You again have to reconsider everything. So now we will start with now the guy who is working on the vehicle control unit now, and who is working on the heating and cooling function. Now he will take care. Okay, now there should be one more parameter which should be go from the vehicle control unit to the BMS, which is actually the cooling variable, I will call. So now second thing, charging allow by VCU. Why it is mentioned like charging allow by VCU? Because I already told, vehicle control unit is a master. He will take care of entire system in your EV. I mean, no matter where the other controller is located, he will just take care. Now he will allow BMS. Okay, this charging allow by BMS. He will allow. Okay, you can charge. Now from the OBC we are getting everything fine. Now you can start charging the battery. Okay, charging allow by VCU. Now request VCU to BMS. So now VCU is requesting BMS. Okay, you can start doing your functionality. So that also be covered by the vehicle control unit only. If you see enable OBC, so it was also controlling the OBC. Now BMS is also controlled by the vehicle control unit. And if I am telling the terms like this vehicle control unit, BMS, OBS, it is just a piece of PCB with IC. I mean the proper IC, nothing but the controller. So don't get confused. I mean these are just the word which is used by the industry, but it is just a simple controller which we used to use in the college. Now the big role will come in the OBC to the vehicle control actually. Now if you see, there are 9 parameters. Sorry. Then the first priority I want to give actually from BMS to the vehicle control unit. I want to give that priority because I just want to ensure BMS health is not good. BMS is sick. So first it will show BMS error. So BMS error will go to the vehicle control. Okay, I am not in the state of doing anything, so I will not charge the battery. So this, if you design very good OBC, still it will not, it will work, but the charging will, the actually our ultimate aim is to just charge the battery, so that will not happen. Then BMS HU on off state. So whether the BMS is on or off, that feedback will be provided from BMS to the vehicle control unit. That also we need to make sure. Okay, I know you are only designing the OBC, but who are working on the OBC from your team, he also have to make sure this parameter to make your system work, because our ultimate aim is to charge the battery. We cannot leave the BMS part. Might be you are telling why I am explaining, but that is really important. You should aware about that. Then BMS HVIL, this is actually one concept actually, the high voltage interlock loop. I mean you just Google it after this session, but I will explain very quickly. This high voltage interlock loop will go from your all the high voltage unit. So who are the high voltage unit actually? So high voltage unit, your BMS, your vehicle control unit, your OBC, then your a battery pack, completely from the battery pack. So make sure that, so I will show where is the make sure that this one, okay, this connector, this DC plus and DC minus, okay, so this is not connected to your BMS. So your HUL will make sure, okay, the connection is not proper, connection because that interlock loop is not happen properly. This HUL is there in every vehicle, if you go to BYD buses, in Tesla, McLaren, every vehicle where the EV is used, where the battery pack is having the more voltage, so this HUL will be used to make sure that everything is proper. Now why the BMS crash status is there? Okay, so your vehicle is getting crashed, okay, and your battery pack is completely crashed. Then BMS will inform to the OBC, oh, it is crashed. You don't know, but is it crashed? Then I cannot start the charging, sorry. Next, BMS charge request, current request. Now BMS will request to the vehicle control unit, oh, this much charge I required to charge my battery. Okay, so if you have aware about the CC and CV, like first it will go to the constant current and then it will go to the constant voltage. So why? Then their BMS will play the role actually to make sure the battery is feeding properly. Then BMS charge voltage request, it will request to the vehicle control unit, not the OBC, because this is the master. It will ask to the vehicle control unit, and then vehicle control unit will ask to OBC, okay, I want this much current, because I already told current OBC request, okay, which is actually requested by vehicle. This is how it is connected. So while you are also working, you have to make sure that this all the dots should be getting connected correctly. Now what is this BMS SOC estimation? The state of charge actually, which will be there on your mobile phone also. So just to show in the percentage whether that how much your capacity is remain in the battery actually. So that estimation, which is actually done by there are many algorithm to estimate the SOC properly. Then pack temperature. Why it is required? Because you have heard of many newses that okay, like the Ola battery is getting fire. The Tata Motors also, one of their vehicle also got fire. So BMS will give a pack temperature to the OBC, to the vehicle controller. Look, my pack temperature is above the threshold. I am not going to charge the battery. So you tell me, you have plugged the gun, you have designed the OBC. Okay, now you connected the charging gun. Now it is about to charge the battery. But now look what happened. Your pack temperature is very high. Your pack temperature is above the threshold. Do your starting charging going to start? No, it will not start because the temperature is not good. Your BMS is not in the the well state. Now the last stage, what is this pack current? Why pack current is important? This is how we will estimate the kilowatt of the battery. Pack current is there. Okay, pack current will be provided to the vehicle controller. Just applying any of the shunt sensor to understand how much we are taking from the battery while vehicle is in the running state, or you can say it is vice versa from the control unit to the BMS. But this pack current, while designing this pack current, you have to make sure that the sign significant, any of the plus minus. So let's sure that you are charging from the OBC to make sure that the pack current is equals to, suppose BMS is taking 10 ampere, so it should be a plus 10 ampere. So just make sure that I'm using one parameter for both the operation. Make sure that now you are running the vehicle where you are discharging the battery pack, then you have to make sure that okay, it should be in the minus. So this same parameter, I will tell where it will play the role. I will just tell you the difference when someone asks that where the inverter, what is the function of the inverter. So your function of the inverter, actually it will feed DC to AC. It will convert DC to AC and work the induction motor. Then your pack current will be a positive. But now you tell me there is one situation which is called as I hope you are aware, which is actually the regenerative braking. In that case, what will happen? Your from your motor, okay, from your motor, now your battery pack will get charged. In that case, what happens? Your pack current should be negative. Just you have to mention the sign as a negative. Okay, it is negative current. Then this is how you can design the OBC actually, step by step, considering all the function thing, considering the all covering all the function, which is like AC charging. Okay, I need AC charging, then I need heating cooling, then I need OBC control, then I am having simple which is actually the black box OBC here, like that. So I hope this is sorry. Sorry guys. So you just have to make sure that you are considering this all the state, because you will design the OBC, but you didn't consider the pack current. So I mean, what is the importance of designing the OBC? You have to make sure that this everything will work properly, and that is what then someone can be recognized. Okay, this is properly done. This is properly, that is which is called it as okay, this is the proper system. It is not like someone just took some component and just designed the OBC. So you please make sure that this everything will be proper. So now from four of you guys have designed this. Now we have to jump, which is more critical part, where even the industry also failed to meet actually now the standards. So next slide is actually your standards, because you will design anything, but it should meet the standards actually. So now if you see, this is I have this rounds are there. So if you see, you connected vehicle to the EVAC, to the charging system. Now your charging is started. Everything is going properly, okay. But now you start thinking like this. what first thing you have to do? First thing you have to do, you have to plug the gun to the vehicle. Second thing, your vehicle and EVAC, you have to make sure that they have a good handshake. Correct? Yeah, you just have to make sure, okay, they have properly handshake. Second thing, now you have to set whatever the parameter you set for voltage current, that also need to be met. So now if you see the first round, this one clearly, which is the plugs, comma, in and outlets. But just to define, just to work on this single function, you have to make sure that you are meeting these all three standards. Okay, now with this side, if you see this 1 2 3, and now one more standard is there, and which is covering our 5, which is actually, and one more is ISO 17409, where coming under the safety because you have to make sure if you're plugging the gun, it is properly plugged, because it will be safety concern. If someone is touching, someone is doing some unnecessary thing, you have to make sure the safety. But for the safety, how many standard we are using? 1 2 3 4 and the 5. You imagine, just to ensure the safety, just to ensure the handshaking, you are using 1 2 3. Okay, now we are coming to the 2, charging topology and grid integration. Charging topology you are defined, okay, it is a CCS2 or it is a CHAdeMO or it is a G by T, you have to make sure. Then charging topology and the grid integration. Grid integration means this and this handshaking. Now you check this round, how many standards are covering. It is already there in the standard, you don't have to think much, you just have to follow the standard, because if you are developing any of the unit, you have to make sure it will follow the standard, it will follow all the guidelines. Then anyone can buy or anyone can appreciate, okay, this is what it is designed. It is not like just playing with the circuit and the program and just define. Then look at the standards, how many standards are coming. This one IEC 61980 part 3, then 1, then 22, 21, 23, and these all also are coming under that. Now I'm jumping to the communication. The communication should happen properly. Communication between the EVAC and this guy should happen properly. That also you have to make sure. So who will do that? Okay, all these standards. If you see, there are, I think, more than 15 standards now including in that. Okay, your communication is properly. Now the last part which is left, security. Why security is also important to play the same role there. So security is also important. Because because there may be chance when you will develop a charger and someone is charging their vehicle without paying you. Okay, so you also have to mention that security also, and someone cannot steal your energy, so that security also. And second is actually your cyber security for sure. So someone cannot steal or someone cannot do your car because your car explode to the atmosphere. So this is what actually the overview of the OBC and how you will start working, how you have to do it slowly, how you have to take the baby step, how you have to define the parameters. So this is the way of working actually, which we follow as a industry, because as an industrial person we follow actually. Whenever we want to define any of the controller, we have to follow this all the step one by one, and there what the one of the unit or any thing will come out actually. So actually this is the last slide actually. Thank you. I mean, if you have any question, you can do ask. Take my mail ID from the organizer. I mean, who is the organizer? If you have any doubt, just put it on the mail. You won't believe we have a very big team even your small doubt or any help is required while developing that, we will ready to help. I mean, there is no doubt. So for here actually I will want to end my session actually.
Thank you, Shubham. Thank you. It was a very informative session. Jason, do we have any questions?
No questions so far. So when they send the questions, we will contact you. Right? We can send them when you share your emails.
Yeah, sure. I mean, you give mail to everybody. I mean, there is no problem because we have very big team here and more talented. I mean, having very more experience in the EV because on the pure EV actually, I am also working on the EV. So the thing is, if anyone having any question, they can do reach to us actually, because I am also connected to my college also where people are participating in the hackathon or Yantra or any of the competition. We are helping them. So we are ready to help. With the free of charge.
Okay, thank you for that offer, Shubham.
Thank you, Shubham. That was very generous of you.
Yeah, thank you so much.
Thank you, Shubham. So Jason, shall we have the next session now, or is it a break?
We'll have the next session. It will be the last session for today, and the rest of the session, which will be a case study, will be shared as a recording to all.
Okay, then I will invite Dr. B. Dastagiri. Next I invite Dr. B. Dastagiri Reddy, who is currently a faculty in NIT Surathkal, for taking presentation on smart grid for BEVs. He has a PhD in electrical electronics engineering from NIT Tiruchirappalli and has abound papers and extensive research experience in power electronics. So welcome, Doctor.
Hi, good evening everyone. I hope I am loud and clear and my screen is visible to you.
Yeah, it is visible and you're audible.
Okay, thank you for the confirmation on this. Hold on a second. Okay, so I hope it is fine. Shall we go? Yeah. Okay, hi everybody. So I hope this is the last session. We'll try to wrap it up as soon as possible, or at least within the timeline. May I know how long I have?
Yeah, Jason, it's 1 hour, right?
Okay, I thought we are running late. 1 hour. Yes. Okay. Yeah. Thank you. So we'll be discussing about EV charging technology and solutions for different solutions. Especially like mostly we focus on e-bus solutions, and then we touch upon integrated solutions as well and wireless charging solutions as well. So this is the overview. So I'll be looking at some profiles of e-mobility research lab, the other colleagues of mine who are working in the same lab. Then just a brief overview of onboard or off-board charging. I hope everybody are familiar by now. Then we jump into the charging solutions for e-buses and some solutions related to the charging infrastructure, like what is existing and what we are proposing. And some integrated charging solutions where you can use your motor drive as a charging, like what and all happening there and what exactly is our contribution from our lab. Then we also touch upon the wireless charging solutions as well. So coming to the profile, as the panelist or organizer has already mentioned, myself, Dr. Dastagiri Reddy. I did my PhD from NIT Trichy and postdoc in National University of Singapore for about 3 years. And then I worked as a scientist at ABB. Now currently working as assistant professor at NIT Surathkal. We also have a startup company called Drive EVs, where we work on various aspects of e-mobility. And overall, I worked on more than like 10 R&D projects, so for 12 patents and 20 plus publications. So these are all some projects that I worked on. And this is Dr. Praju, who is my colleague who joined along with me, PhD from IIT Bombay, who worked as project lead at LTTS Bangalore, and we both joined together, and that's how we started this lab called E-Mobility Research Lab. And another colleague of mine, Dr. Dharawat Kishan, who has done PhD from NIT Trichy and expertise in wireless charging. He is also part of the E-Mobility Research Lab. So jumping into the topic, this is the architecture of pure EV, where you can see there is a battery where we need to charge this particular battery, because this is the main source of our powertrain. The powertrain is where the power from the battery flows from the battery to the wheel. So this entire stream is called the powertrain. So once we ran out of the battery, then we need to charge our battery. So that is what we are going to look at it. And there are different solutions in that. I hope everybody is aware of by now. But just to give you the power electronics part of it, yes, we have a three-phase inverter, and this is where we generally try to bring in integrated charging, where you have a three-phase inverter there. Mostly three-phase 3-leg or three-phase 4-leg, depends on the vehicle. And we may have multiple motor drives, like we may have 2 or more motors as well in the same vehicle, and they coordinate so that we can control the vehicle in much better way. Of course, the control complexities are there, but still, there are people are looking for 4-wheel drive, 2-wheel drive. If it is a heavy bus, then we need 2 motor drives instead of 1 motor drive. So that is where you get more options in reconfiguring the existing 3-phase inverter into multiple categories, so that you can better utilize the power converters available on board or off board, right? And we have motors, like as you are aware by now, mostly we use BLDC, PMSM based, mostly permanent magnet based. Some companies are looking at SRM, but it's not commercialized yet. And some are happy with induction motor, and some are going with CNRM, where you can have permanent magnet assisted synchronous reluctance motors. So different motors are coming up, so there is a huge scope of research in that areas as well. And then coming to the other side, where we need to have auxiliary power supply, so we generally go with a low voltage battery, and as you can clearly visualize, this is a high voltage batteries and these are low voltage batteries, so definitely we need some kind of DC-DC converters here. So that is also one of the power converters that we need on board. And then coming to the charging of this battery, there are 2 options, as we already know, like onboard and off-board charging. So it is very simple. What is the onboard charging, off-board charging? So at the end of the day, we convert the AC supply that we all have and convert that into a rectifier. Rectify it becomes a DC. So basically, charger has AC to DC and DC to DC. So there are 2 phases. And in this, why we need DC-DC? Why can't we just go with AC to DC? Yes, there are options people are exploring. That is because you need to see what is the voltage level of the battery and what is the voltage level of your AC supply. And when you convert, for example, if you have 230 volt AC, and when you convert to DC, the minimum you get is 320 volt DC, somewhere around approximately. So if you use active rectification, where you can control this 320 to somewhere around 450 volt DC. So if your battery voltage falls under this category, then you don't need a DC-DC converter. So it's all about matching the battery voltages and current. So if you can do that with the rectifier itself, then you don't need a DC-DC converter. Basically, you can manage with AC to DC converter itself. But most of the electric vehicles fall under different voltage ranges, less than 100, like 70 volt, 72 volt, 60 volt, or in between like 200 volts. Some are in 400. Now, most of the electric vehicles are moving towards 800 volts batteries, like especially high-end cars or heavy vehicles like heavy bus or trucks. They are planning for 600 volt to 900 volts batteries. So in that case, When your AC is of either 230 or 415 or 115, then definitely we may end up in rectification stage and DC-DC stage. And I hope everybody is aware of when you are doing this AC to DC conversion, generally our converters will come into picture. There will be some kind of non-linearities, and that is where we generally get so-called grid code. So where whatever you connect or whatever you draw from here, it needs to follow some kind of grid code, that is IEEE 519 or EN 50160. So different standards, mostly follows in the same category. So overall, to summarize the grid code, you will be having a TST current, power factor, and if you are using a thyristor based thing, then you will have something called commutation nodes. Okay, so commutation nodes. These are the major things. But if your TSD is high and if you're not meeting these things, then you may end up in getting TSDV as well. So generally TSDV is the headache of the distribution guy. So he is supposed to manage the TSDV. The supply voltage what you are getting should be of within this limits, which is somewhere around 8%. Depends on the voltages less than 11 kV. So mostly 8% above 69 kV or something, then it will be around 3%, 2%, depends on the voltage levels. TSTI depends on two factors: what is the installed capacity and current using capacity, and what is the installation capacity to the ratio of what is the total short circuit capacity available at the grid. So that is where you just vary this. Okay, it's not like 5% is fixed. Okay, so this is not 5% is fixed. It depends on certain factors, certain ratios. So generally it varies. It's not exactly 5%. Okay, so whenever you come up with the charging solutions, generally we need to, first thing we need to take care about is the grid code. Okay, so that is where our different power converters are coming into picture. So if it is just a rectification, we can simply use a diode bridge. We can simply use some other simple rectification stage where we don't need to end up in so many things. But here we are wide with IEEE 509 grid code and some requirements, general requirements like the weight, volume. These things are also will come into picture, and that is where we end up in different topologies. Right. So overall, we have two kinds of charging: onboard charging and offboard charging, where your entire charger, for now, will take it's AC to DC plus DC to DC. So both converters sit on the board, like on the vehicle. In other case, you convert AC to DC and DC to DC. Everything comes in a box and which is sitting outside. And this is where you get off-board charging. So the major difference what you get is the communication protocol. So if it is an on-board charging, basically the DC-DC converter is what needs to be communicated with the battery. Because once you convert AC to DC, and the next job is the DC to DC, that is where you need to match the voltages. So basically you have to communicate with the battery, like currently what is your voltage, what is that current that you are expecting. So that is where this DC-DC converter will get its references as voltage reference and the current reference or I reference that it needs to set. So basically you are getting a references for your closed loop control. And that is where you need mostly the communication. And when the voltage or current, or in other words I will say SOC reaches a certain level, then the same BMS will communicate to the DC-DC converter, change your reference or change your mode from constant voltage mode to constant current mode, or constant current to constant voltage mode. Similarly, these things will be happening. So basically for your DC-DC converter, if you are a power electronics guy, you know that there is a need of closed loop control and there is a need for references. That references is what you are getting from BMS through communication. Okay, and that is what actually happening. When it comes to DC fast charging station, as your AC to DC and DC to DC, everything is off board. So definitely you need a communication here, so that this general purpose DC fast charging station, which is generally varies from 200 to 900 volt DC. So you can get 200 volts to 900 volts DC. So if vehicle 1 comes, it may need 400 volts. Vehicle 2 comes, it may need 600 volts. So definitely first thing first is to know what is the requirement of the battery, and that is where the protocols will come into picture in DC charging. In onboard charging, protocols still exist, but when it comes to the contact, like it is just a plug. Like you connect your charger to a socket and your charger takes care of what it needs. Like your laptop charger, the same plug point you connect your mobile charger, it doesn't make much difference. So you don't need any communication to the socket and the plug that you are connecting. But when it comes to DC, a protocol is must. Okay, and the protocols generally categorized as 4 now, as of now. But whatever may be, whether it is CHAdeMO or CCS2, CCS, anything, overall it happens like this. So you have some kind of handshaking. As I said, if there is a DC-DC converter, you need some parameters to set your controller. So you need to understand what is the current SOC, what is the requirement of the voltage, what is the requirement of current, so that you can adjust your DC-DC converter. Then a charging preparation, once you get that signal, you'll get the preparation, like you fine tune your references and then start your PWM signals, everything, all you're ready. Before that, you just have to be ensuring the plug is properly connected or not. The earth loop check will happen. Those things will happen in this particular iterations. Then actual charging starts little later. So generally this needs roughly about 30 seconds for heavy vehicles. Okay, and then after the energy transfer is over, finally you go for shutdown. The shutdown also, you can't simply shut down, but it has to follow the same process. Like you have to stop charging first and then make sure the charging is completely stopped, there is no current going through, then only you can break it. So it's all some electrical safety point of view and communication point of view, like money transaction point of view. That is where there will be little delay even at the shutdown process as well. So this is how generally it works, whether it is CHAdeMO or GPT or CCS2, anything. Overall, this is what it is going to happen. So because you are having a general purpose charger where it can give a wide range of voltages and wide range of currents, and it is your duty to check with the vehicle what is that it is required, and then accordingly you set your control parameters or reference parameters and then start charging. And before that, you need to cross check whether the connection is proper, whether the earth loop is properly connected or not, and everything. Okay, that is where you get this protocol, and this is majorly important for DC charging. Onboard charging, the communication, everything is properly taken care, and you don't need much there in onboard charging, because the onboard charger is dedicatedly designed for that particular battery that you are using in your vehicle. So the communication protocols are of, it's required, but it is of less priority when compared to the DC charge, right? So then coming to the e-bus charging. Okay, before jumping into e-bus charging, why e-bus charging is so important? Like why it is different from regular charging? Okay, we know charging consists of a rectifier and a DC-DC converter. What difference it makes? So difference what it makes is bus is a huge vehicle, and the energy what you need is very huge. Okay, how it works is, for example, if there is a depot having 100 buses, you have 100 buses, diesel buses. Okay, now you are happily running them. Maybe your operation time may be 18 hours. Okay, so 18 hours you can run. Even if it run out of diesel, you go to a petrol bunk and you can fill it in 3 minutes, maximum of 3 minutes, or even 1 minute, 2 minutes is possible. Like let us take 3 minutes. Okay, and that is where you are able to meet your requirements, city requirements for 18 hours of operation with 100 buses. But if you change that bus to electric buses, like can we manage e-buses of 100 and get the same is the biggest question mark. That is because the filling time, tank filling time is no more 3 minutes. So we may end up in buying 150 or 120, sometimes 200. So this is what called replacement factor. If at all you want to replace the entire depot of diesel buses into electric vehicle or electric buses, then we need to think about the replacement factor. That is mainly because of filling time, your tank filling time, or indirectly you're talking about time taken for charging. This is huge, and that is where we may end up in buying more buses. And what is the problem in buying more buses? Expensive, first thing. And when it comes to current diesel buses, it will cost somewhere around, a luxury bus will cost around 1.5 crore, let's say. With the same luxury, if you want to buy an e-vehicle or e-bus, it is going to cost you somewhere around 4 crores. 3.5 to 4 crores. So that's a huge difference. And that is because almost like 40% of your e-bus goes to battery. So 40% of the dollar is going to the battery alone. And this battery life, mostly people are promising from 3 to 5 years. So that means after 3 to 5 years, roughly you need again 50% of your initial investment again after 3 to 5 years. And that is where the biggest challenge when it comes to e-bus charging. It is not as easy or as simple as your commercial vehicles like cars or your own personal vehicles. So charging management for e-buses is a little tricky because of all this. You can't replace every bus into this. So even if you replace 100 buses of electric buses, then how you manage a depot? So you need a huge setup at your depot. For 100 buses, you need 100 chargers. So 100 chargers, okay. It's obvious 100 chargers. Why not 100 chargers? Why 100 chargers? That is where the first question comes in. Then if you say 100 buses or 100 chargers, then where will the entire power come? Again, you need to think about a transmission line. Then a step down transformer. Like if the buses are more, then you may need a bigger power requirement. So the bigger power requirement does not happen with 415 volt buses. You need to go for 66 kV transmission line. So a separate transmission line, then a step down charging station, substations, everything is required. So you need to do a lot of modifications. If at all you take a decision of replacing 100 diesel buses to 100 electric buses, you need to think of multiple things. And that is where it is not easy task to replace buses, diesel buses to electric buses. So to handle this, there are 3 different solutions in the market as of now. So, but before jumping into that, let us understand what is the requirement of the energy. Okay, we all know the basic definition of power is E by time, energy by time, and that will give you energy is power into time. So when I say energy, so what I'm talking about here is what is the energy that I need for a bus to move 1 kilometer, and that is generally estimated as this much. How you get that one? So we generally get it from F equal to ma plus the other forces, climbing forces, dragging, aerodynamic drag, then rolling resistance. So basically add all the forces. Then you multiply that with the required velocity. Force into velocity will give you the power. And then once you get the power and how long you need to run it, and that is where you get your total energy requirement. And people will add upon the drive cycles, like we can't have a constant velocity. So generally to get this one, we go for different drive cycles. So you incorporate drive cycle, city drive cycle, urban drive cycle, highway drive cycles, and then finally somehow you manage to get this number called energy consumption rate per kilometer, energy required per kilometer. So for example, for a 12-meter bus, on an average it comes around 1.5 kilowatt hour per kilometer. So this bus has to have a mileage of 300 kilometers in single charge. That tells you your battery should be 300 into 1.5. So that is not enough, because for 300 kilometers you can't drain your battery. So we need some kind of buffer. So we generally go for 1.3 or 30% is extra. Somewhere greater than 450 kilowatt hour is what you need. Greater than 450 kilowatt hour is what you need, the total energy of the battery. So that is what the battery size we are talking about. So that's how you can estimate, right? So once you know the energy, then our job is to decide what is the voltage and current levels. So generally, if it is a low energy, low power, we start with the lower voltages because of the safety standard. And as the power increases, then we can't manage the current cable sizing. So generally, we increase the voltage. So that's how we play a role. Like start with lower voltage and see what is the current. If the current is too high, then you increase the voltage so that the current will come down. So finally, we come to a conclusion: what is the voltage and what is the current, where you can balance. So generally, we go less than 1 kV voltage, 1 kilovolt. That is because the safety standards will go high once you cross 1 kV in DC, 1 kilovolt in DC. The safety standards and the switchgear and protection equipment will be very tricky. So that is where most of the electric vehicles will fall below 1 kV. But now GBT is talking about 1.5 kV. Of course, there is some development in the DC switchgear as well. So there is a possibility of going above 1.5 kV or up to reaching up to 1.5 kV. But as of now, it is less than 1 kilovolt. So that's the battery voltage I'm talking about, right? So that's how once you get the energy consumption, then you estimate what is the kilowatt hour per kilometer. Once you know that, you know the mileage, like single charge, how many kilometers, accordingly you design your battery. Once you know the battery, now comes the charging time. So once you know this energy, then you need to fill this energy with certain power. So that is where energy is power into time. So to reduce the time, our job is to increase the power. So it is very simple. So if you want to fill this tank capacity much faster, so that means if you want lower time, then definitely your power should be high. That's all. That is what fast charger is doing. So fast charger is nothing but increase the power rating. So what's the problem in increasing the power rating? Why can't we increase the power rating just like, because anyway now we are talking about HVDC transmission where we are talking about megawatt or gigawatt level converters are there. So why can't we just one converter and charge our batteries very fast? That is because there is a limitation from the battery side. Okay, we don't have any issue to build a converter of high power. The power electronics are now supporting. The technology is in place. We are talking about multi-level converters, modular multi-level converters. Many things are available. So constructing a converter of high power is now possible and it is proven. But only problem what we have is the battery is not accepting that much power. And that is where your C rating is coming into picture. Okay. So basically when you look at the battery, there are two ratings, power rating and energy rating. So energy rating is very simple. It's tank capacity. So bigger the tank size, bigger the energy. Very simple. And the power is valve opening. Okay. So if the valve is opening is more, then you can fill it faster. If the tank size is more, but the valve opening is very small, then you need more time to fill it. And that is where called the C rating. Okay. So as per your general formula, power into time, to fill your battery much faster, you need to increase the power rating. The problem with the charging or fast charging is your C rating of the battery. So which is a fast charger? Let's say if I say 300 watt is my charging power. Is it a fast charger for a mobile? Yes, for a mobile it is a ultra fast charger. Mostly we are having 25 watt charger itself. We are saying it is a very high power charger. But if I say it is for four-wheeler, 300 watt charger is a slow charger. Okay, so the fast or slow, we need to define or we have to define based on the energy rating. For an energy rating of lower energy rating, high power, high power charger or fast charger is different. So the definition changes based on the values. So this formula plays, right? And that is where you have a C rating. So now there is no magic in the fast charger. It is simply you are increasing power rating. If you can increase the power rating of the converter, the problem is the battery C rating needs to be taken care. Why can't we buy a high C rating battery? Basically now it is not available as of now, but reasonable C ratings are available in the market. And if at all if you want to increase the C rating, there is one simple way. So let's say it was given to you, and I say that its maximum capacity is 5 ampere, and you can't go beyond that. But I want to carry 10 ampere. What is a simple solution? What you can do? You can add one more wire, and you can finish your job. That is one way. The other way is you bring in cooling, and when it gets heated up, you try to increase the cooling, and you can carry 10 amperes. Whichever is convenient, whichever is economical, you choose that option. And that is what we are doing with battery as of now. But paralleling batteries is indirectly affecting the energy rating. They are not separate. So there is no decoupling between them. They are somehow linked together, and that is where the problem comes. So most of the high power batteries comes with cooling, so that you can have little more push in the power or little more increment in the C rating, or some battery chemistry itself. Some people are working on. So far in the market, there is something called LTO batteries, which is highest C rating. They are offering very highest C rating. But the problem with this battery is the voltage is less. The cell voltage is less, but it can give very high C ratings. Okay, so this is where the battery chemistry will come into picture. So the problem with the charging is battery itself. There is no problem with the power converters, right? So when it comes to the storage elements, there are two things. As I said, power is there and energy is there. So power density and energy density there are. Basically, right now, electric vehicle market needs some kind of storage unit which is in this area, which has high energy and high power, which is not possible. So that is where we have seen lead acid, very high energy, but the power is very low. So that means you charge them very slow. It can't give high C rating, it can be very slow C rating. So somewhere reasonably having energy density as well as power density is lithium ion battery, and that is what we are using. When it comes to ultra capacitor, it has a high power rating, but it has very low rating. And there's one more issue: the voltage stability is an issue with ultra capacitor, because the moment you start discharging, the voltage vary across the capacitor is very huge. So that means your converters that you're working with the super capacitors should have a very wide voltage and current variations, which is a little tricky. Okay, and this is what the actual problem. The problem is with energy storage. But we have to move further, and we need to somehow find a reasonable solutions, and that is where we need to go for different strategies of charging electric buses. We can't wait for a technology that can go in this area where you get high power rating and high energy rating, so that our problem is solved. But yeah, some people are trying there. But for the existing technology, we need to come up with certain ideas where you can solve the existing problems. Right. So you might have come across there are different ways of charging: 6CV, MCC, 4C, 1C, pulse current, sinusoidal, whatever it is. At the end of the day, we are trying to safeguard the battery or to stop it go to a stage called thermal runaway. Okay, the state called thermal runaway, where the battery blasts or catches fire. Okay, and that is where you get different charging methods. So basically the problem is in lithium ion, mostly you have a separator and you have some slots on the one side, and you have different kinds of slots on the other side, like two electrodes, anode and cathodes. So basically the lithium has to leave one electron, and the electron will travel outside the battery, and the lithium plus will travel inside the battery. As you know, there is a imbalance in the weight. Electron is very light guy, and lithium plus is little heavy, and somehow they have to reach at the same time, which is not possible. Okay, and this guy has to go and sit in the slots. Okay, there may be slots like first in, first last in, first out. So it depends on the slots. So based on the arrangement of slots, you get C rating. That's the chemistry side of it. Just to give you an idea, so the lithium leaves electron leaves the lithium and travels outside the battery, which is the basic circuit available on the battery terminal between the two battery terminals, and the lithium ion travels internally. So as you know, there is a speed difference, and that is where we end up in having different arrangements inside the battery. But even if you have a C rating telling you, let's say the C rating tells you can have 100 watts of power continuously, but that is not true for entire SOC range. So in the entire SOC range, your C rating will not work in the same range. In the beginning, you have to be little slow, and then from, let's say, comfortably from 20 to 80, you can fully give this power. Okay, where slots are free, the lithium ion can move here and there, the mobility can be free. But once it reaches a certain stage, somewhere around 80 or 85%, you need to slow down. You need to slow down because this lithium has to go there and catch the incoming electron there. So the ion accumulation will be more when the SOC is reaching 85% or 90% or 80% in some batteries, and that is where you have to slow down, and that is where we enter into a mode called CV, where the current will be drastically reduced. Okay, and that is what the limitation. So we can use the C rating only in the range of 20 to 80%. As a thumb rule, we can say most of the batteries will fall under this category. So from 20% of SOC to 80% of SOC, you can use the entire C rating given to you, provided the ambient environment supports. Okay, there are some temperature limits as well. Okay. And when it comes to voltage, why the protocol is very strict on voltage levels is, as you know, there are two electrodes which is acting as anode and cathode, and there is a separator. Though your anode or cathode terminals are capable of handling high voltages, but your separator doesn't have that much capacity. So if you increase the voltage beyond certain value, then the separator will get fail. And that is where the voltage limitation is also important. So current limitation because of ion accumulation, voltage limitation because of some issues with respect to the separator and electrolyte available there, so they cannot capable of withstanding very high voltages, and that is where we end up in so much limitations when it comes to charge. Okay, at the end of the day, we are trying to safeguard the battery, which is as of now very expensive. Right. So now we know the limitations. So we know that charging is like you need to increase the power rating. Basically, that is not possible as of now because of limitations with respect to the energy storage device, especially the battery in the current scenario. So knowing this, let us see what are the different solutions we have. So we have overnight charging or depot charging. So that means you bring the bus in the night and full night you charge, and then throughout the day you use the buses. And there is opportunity at terminal charging. Just to give you a rough idea, let's take a city and a depot is somewhere here, and there is some number of buses, let's say 12 buses running between cities and let's say railway station to airport. Okay. So in between there are multiple stops. So this is what bus stops. And this main stop, railway station to airport, the bus throughout the day shuffle between these two. It starts from railway station, goes to airport, and airport to here. So this railway station and airport in this example called as terminal. Okay, this is terminal and this is terminal, and this is the depot, and this is bus stop. Okay, so first one is you charge only at the depot and let the bus go any route. There are multiple routes in the city. Here one route, one more route here, one more route is here, one more route is here. So multiple routes, but everything starts from the depot, and throughout the day it roams between two terminals and come back. So now, if you look at the buses, how they operate is once they reach the terminal, final stop, they won't immediately return. So they generally wait for 3 to 6 minutes. So why to waste that time? Why can't we charge? And the terminal are opportunity charging. Like wherever you have an opportunity of charging, you charge it. And that is what opportunity charging. Okay. Then Anyway, you are charging at two terminals. Why not at bus stop? And that is where the flash charging is coming into picture. Bus stop means, sometimes bus stops or sometimes bus may not stop. Even if it stops, we don't have time. Like, we don't know whether it stops for 1 minute or 10 seconds. The passengers of more, then you can wait for long. So that is where you enter into flash charging. But what are the challenges, or let's say, what is the trade-off that you get between these two? Okay. So let us understand. So, for example, if you go with the depot charging, let us consider a 300-kilometer scenario where you need a battery volt capacity of very huge capacity of 450 kilowatt hour. Okay, so for this bus to run for 300 kilometers in a day on an average, then you need to buy a very big battery. So bigger battery, bigger cost. Already you purchased so much big battery, so that means weight is more. Okay, your weight is also very high. Somewhere around 5 tons or 6 tons is the dead weight of the battery. So if the weight increases, F equal to MA, so your mass increases, so your overall mileage also may come down. So we may have to increase the battery. Because you purchased a very big battery already, you can't afford a high C rating battery. So high C rating battery you can't afford because battery is very big battery, and if you go for high C rating battery, definitely it is, so you can't buy that, and that is where you end up in buying a low C rating battery, and that is where you buy a charger of very low power, and that is why you need long charging hours. So energy is very huge, and the power, because you can't afford a C rating battery. I mean, if you are rich, you can afford, but if you look at the techno-economic evaluation, it is not a good idea to go with high C rating battery for this kind of heavy batteries. And that is where we always end up in a low power charger or low C rating battery, and that is where your time is high. That is why you get 6 to 8 hours of charging in depot charging solutions, right? And opportunity charging, yes, you need 300 kilometer range, but instead of giving a big fee into time, what you are giving E1 at the depot, and next terminal you are giving another ET and another ET. So it is PT into TT. The PT is like time at the terminal decided by your operator, and P you can decide on the C rating of the battery. Because the bigger energy what you need, the total energy you are getting from depot plus every terminal, like in a day, let's say it takes 10 turns. So it's 10 into ET, then another 10 into ET. So your energy you are bringing in between. So that is where you can buy a lower tank capacity. So your battery size will come down. Because you are buying a lower energy rating of the battery, you can afford a little bit higher C rating battery, more or less same price when compared to this or this. Here the C rating is less, here the C rating is high. Because you purchased a high C rating battery, you can charge it faster. Here the energy has come down, power has increased, so that you can charge it fast, and that is where at the terminal within 3 to 6 minutes you can charge. At the depot you can still have the same slow charging as per your requirement. And the third case, the bigger energy you are getting from multiple instances. You are getting from depot, you are getting from bus stops, you are getting from terminal. So multiple terminals, multiple bus stops. So you can further reduce what is the battery that you are going to buy. Since you are buying a smaller battery, you can afford a bigger C rating battery, so you can charge more faster. Okay, more fast. And that is where when you go for depot charging, the run time, like operation time, will be less. You can't operate in, let's say, 12 hours or 14 hours is what maximum that you can expect in depot charging. Terminal charging, you can go up to 16 hours of continuous operation. Flash charging, you can go up to 24/7. I'll tell you how to do that. Okay, so in overall, as of now, I just mentioned about weight point of view. So what is the weight of the dead weight of the battery? That I have discussed. And then dollar of the battery I have discussed. And then something called C rating of the battery. So based on this, you can manage your charging, right? So if battery weight reduces, it is good for you, the mileage increases. Dollar, when it comes to dollar, if you are going for a bigger battery, low C rating, same price, little lower capacity of the battery, bigger C rating, more or less same price. Small battery, very high C rating, more or less same price. So overall, it is same battery dollar point of view, more or less. But what the benefits that you get is you can get more operation time. Your time required for the charging at the depot is coming down from the top to bottom. Okay, so that means instead of buying 120 buses because of charging, you can buy 80 buses because we don't need to wait for charging. Okay, but when you look at the last option or the second option, anyone can ask an obvious question. If you are charging battery very frequently, what happens to the life of the battery? Is a question mark. And you are increasing charges, no? Instead of having one charger at the depot, you are buying so many chargers. So what about the cost of the charging infrastructure? So these are the two biggest question marks when it comes to this. Organizers, please let me know if I'm running out of time in between, okay? May I know how long I have more?
You can take another 15 minutes.
Okay, fine. I'll try to.
Yeah.
So when it comes to the life of the battery, there is something called charging cycles. Everybody knows that charging cycle is something you need to be taken care. But there's one more important thing that is called depth of discharge. I hope everybody knows about state of charge and depth of discharge. It is just reverse, right? So let's say you are having a battery and you are using it like this. You start from 100, goes to 0, and slowly you charge it to 100. Again, you discharge it, then charge it, then discharge it, charge it, discharge it. It's very good. Your cycle is not disturbed, and your number of cycles are under control. So people think that you get more life, but it's the same thing, the same pattern. But instead of having discharge up to this, if you go with let me change the color so that if you go with 100 to 50 and charge it, then 100 to 50, not 100, maybe here itself, something here. Okay, so the green one, let's say this gives a warranty of, or the life comes of 5 years, and this one, the green one, will give you 2 to 3 times of years. Okay, so the depth of discharge plays a major role in life of the battery, and that is one of the key aspects. Second thing, when you look at the 3 different options what we have, the first option, we have big battery, we are discharging it only once in a day and we are charging it once in a day. So the number of cycles that you need is very less. But when it comes to terminal charging, so that means when you come from railway station to airport, one trip, here one charge, here one charge. So in a trip, you are doing 2 cycles. You are using 2 cycles. In a day, if you go for 10 trips, then it will be 20 cycles that you are using. Okay. I hope you know the battery chemistry. So nowadays, like if you go for high C rating battery, the number of cycles are also more. It is coming up like that. So the number of cycles generally comes as per the structure of lithium-ion battery. As I said, there is a separator and there are some slots available here for you. So this is like you buy a very quality sponge and dip it in water and compress, then again dip it in water, then again compress it. How long it can stay without losing its shape? You buy a very cheap quality sponge and dip it in water, and within 10 times it will go. That is what I'm talking about. This cycles generally talks about you are releasing lithium and you are attracting lithium plus ion. You are accommodating and compressing. So that is where you are squeezing kind of, and that is where the material will be coming into picture. So now most of the high C rating batteries are having higher cycles as well. Okay, so if you buy a high C rating battery and using like this, your cycle may be longer, but overall life will be same, right? So, and that is where when it comes to flash charging, what you are doing here is between the terminals. So when you start at railway station and reach at airport, you are completely discharging it. So instead of doing that, can you limit it to 50, between 80 to 50? And that is where your bus stop charging comes into picture. Just limit the depth of discharge. You introduce some charging in between so that you don't discharge deeper. And that is what happening in the third option. Why we are doing that? To enhance the life of the battery. And that's the purpose, right? So this is what exactly happens in the real world scenario. You start with 85. Don't charge at 100%. As I said, in this region, you need to slow down your charging. Why to slow down? Why to waste my time? Anyway, I'm not going to use the entire battery. I'm not going to drain it. So you charge it till 85%, use it till 50%, and then again charge it to 85%. So you play with 40-80. Okay, mostly like 40% to 80% SOC. Your life is very good. You can enhance the life weight 2 to 3 times. And that is what's happening here. Now, second question what we had was, it's about infrastructure. So how you can address the problem of your infrastructure cost, right? And that is where your integrated charging will be coming into picture, right? So if you use normal driving, there is a motor drive, you're connecting to the battery and running your motor. When you go for conventional, your charger, your rectifier and DC-DC converter, you are bypassing this internal converter which you already purchased and you are not using it. And that is where you can reduce the infrastructure cost. If you can utilize your onboard converter as a rectifier and a DC-DC converter, or inverter come DC-DC converter, and instead of charger you can install only a rectifier. It is a DC plug point. Instead of AC plug point, you get a DC plug point of 500 volts DC or 600 volts DC. Okay, so that is what you give here. And what is the other benefit that you get apart from saving the cost of DC-DC converter? So you don't need DC-DC converter anymore. But when you look at a charger, high power charger, the cost of rectifier is cheaper than the cost of DC-DC converter. So now you are eliminating a DC-DC converter, but you are coming up with only a rectifier, and you are maintaining just a constant DC bus. You are not doing anything, no control. Just maintain the 600 volt or 500 volt common DC bus. That's all. Okay, and that is where you can save cost of infrastructure. The other thing what you need is protocol. When you are using your onboard offboard converter, then you need to follow the protocol very strictly, because the battery, we don't know what is the voltage and what is the current that requires. But if you use your own onboard converter, you don't need any communication to this rectification station. So you can avoid CCS2 charge demo and everything, and you can charge immediately, because when you stop at a bus stand, and if you have to charge for 10 seconds, you have to wait for 30 seconds to complete this so-called protocol setup, and then you have to charge for 10 seconds. So that will be 40 seconds total. Now, if you can use your onboard converter as a charger, you can eliminate this 30 seconds delay. The moment you connect, you can go ahead. And that is where the pantograph solutions, robotic arms will play a major role in connecting it very fast. You connect in 1 second, you charge for 10 seconds. Already 11 seconds, that's all. But if you go with protocols, then 1 second for connection plus 30 seconds of protocols, it will be too much. We can't save that much time, right? And that is where the integrated charging plays a major role, right? So overall, when it comes to the infrastructure, you have a rectification station, not a charger, and your battery is oscillating between 80 to 40% so that you can get the more life of the battery. It is very good. infrastructure cost is reduced, battery life is increased, so everything is under control. And that is how the flash charging technology will work better. It was a product of ABB, now Hitachi Energy. Okay, so you can Google or YouTube, just type TOSA, you'll get more details about this particular product and how it works, right? So now, the major impact on the charging of these buses on the utility grid, how it affects. As I said, when you have a depot and you want to charge everything overnight, let's say 3 hours, simple numbers are given here. Let's say there are 250 kilometer range buses are there. So you take this number, 250 kilometers. So this is the energy per bus. And if at all you want to operate for 18 hours, okay. In flash charging, you are charging the buses on the road, like while operating hours. Okay, so that means you see a flat curve of 3.5 megawatt in your existing utility structure. But if you go with overnight charging, you get a huge peak for 3 to 5 hours, and rest of the day you are not charging anything. And for this 20 megawatt, you need to bring in medium volt transmission lines and then substation, then install all the chargers. So you need to do a lot of work at your depot to accommodate overnight charging, and it will have a huge impact on the utility grid. Right? Same thing with the different numbers. Like you say that I don't charge only in 3 hours, but I distribute my charging profile in multiple hours. Or first I bring in 50, then I bring in 100, then after that first 50 leaves. Even if you do, it will be 12.5 megawatt, which is not good. So if you use flash charging technology or on-road charging or charge while operating, then you get a flat curve in your utility grid, which is good for your entire grid. Okay, so these are the live examples of this technology running. One is in Switzerland, where it is a length of 18 meters. It can carry 133 passengers. As you can see, out of 50 bus stops, only 12 bus stops are having charging, that DC bus available there, so that you can charge 600 kilowatt in 20 seconds. And another example is in France, Nantes. It's a 24-meter bus. 22 buses are there. 6 places within the 2 terminals. You have 6 chargers. You can still count it. There are 6 here. 1 at one terminal, 1 more at another terminal, maybe 1 at a depot for 22 buses. Okay, so you can count 6 plus 3, 9. Even if you add 1 more, like 2 plus 2, maybe 10, another 2, 12. So 12 chargers, 12 rectification stages for 22 buses. So you're not even buying same amount of chargers, like 100 buses, 100 chargers, not required, not necessary. You can further optimize a bit, right? And that is what the benefits that you get. So with the existing limitations what we have on the energy storage point of view, this is how we can plan our city buses. Highway buses also we can manage similar fashion, but we need to do some math, right? So coming to the other side of the story, like charging stations in general, we have a huge market for charging stations. These are leading manufacturers. So many EV owners are coming up, but still they don't have access to charging stations, and we know there are level 1 charging, level 2, level 3 DC fast charging. But when you go for high power charging, there's a huge cost involved there. Okay, you can see there's a huge cost for 400 kilowatt. And current market, generally you are bringing so many chargers and placing it in one particular location, and you are calling it as a charging station. So basically every charger consists of a DC-DC converter and a rectifier. So you are buying so many rectifiers and so many DC-DC converters, and the utilization rate is going to be very less. And that is where we proposed a different solution. When it comes to Indian scenario, you can see so many press releases from FAME 2, especially on the bus, and FAME 2 especially focuses on charging stations. Okay, and these are all the standards they have given. So what we have done is we have proposed a common rectification stage and a downstream IGBT converters which can act as AC charger or DC charger. And this is what the solution we proposed, and we got funding of 60 lakhs from Department of Science and Technology, and the technology has been patented and we are in discussion with industries. So as you can see, when you say common rectification, say the reliability should be more, grid code should be comes into picture. We need to see the cost and volume. The cost, when you look at IGBT for 1 megawatt range, IGBT diode bridge for 1 megawatt range, the diode will be very much cheaper, even if you include 3-winding transformer. Because for 1 megawatt, this AC bus will be very high voltage, and the DC bus what you need is low, so you need a step down transformer. So anyway, you need 2-winding transformer. So instead of 2-winding, you bring in 3-winding. So cost won't be much difference. But when it comes to IGBT, for 1 megawatt, cooling requirement is much higher. And when it comes to diode or thyristor, you get cheaper. Like you don't need that much space or cooling requirements. It can work in any environment. But the problem is grid code, and that is where we are working. How to meet grid code with diode and thyristor without having any active or passive filter. That is what the technology we are building up here, and that's the novelty of the project. And the downstream IGBT converters are there where you can integrate. You can configure as AC to DC to AC or DC to DC. It can act as a DC charger or AC charger. Right? This is what the concept, and this is the patented concept. We have done some benchmarking. As I said, grid code is most important, cost and volume wise. The proposed modified thyristor is having a very good results. Like you can have 50% is cheaper and 20% is lower in terms of volume. And these are some results captured showing that the grid code, the power factor in the center, TSD-I outside and TSD-V inside. So everything is meeting in standard. Okay, so then integrated charging, yes, we also working on integrated charging. We recently got a granted patent, and we are getting so many offers from different companies, tier 1 companies and OEMs for this patent. So what we have done, we utilize the motor drive as the charger, but there are multiple research available in the literature. What is that we have done is we are not disturbing anything in this internal circuit. That is what the novelty we brought in. For example, if you have an inverter of 3-leg, most of the integrated charging papers, if you see in the literature, they try to break one leg. For example, this 3 legs. So you include one switch here, and you try to make some modification here between the legs. So this kind of things we didn't do. So what we have done is you have a box, you have 2 DC terminals and 3 AC terminals or 4 AC terminals. We use only this and try to manipulate this one. We don't touch this. So this is intact. And that is what the novelty here, so that you can retrofit the existing EV without onboard charging. You can bring in and we can modify that as a smart charger. Like your normal port TV can be converted into smart TV by plugging Amazon Fire Stick or Apple TV, similar fashion. So we are introducing a proposed coupling circuit, and that box will be fitted so that you can modify your existing car into a smart car. This is the topology. I think we don't have much time to explain how it works, but this is how it works. And then we also thought about now 2-wheelers are coming up with having a 2 battery storage instead of 1 battery storage, and then how the onboard or integrated charging works with the 2 energy storage, and that is where we worked out on another concept and we filed it as a patent, and it is under pending. Then we know that most of the single phase AC to DC has a problem called active power decoupling, and that is where you get 100 Hertz ripples or double frequency ripples. And to compensate that, generally we increase the DC bus voltage. And now some autos are coming up with solar integrated, and some cars also coming up with solar panel integration. So where we need so many converters. So what we have done is we have come up with a multi-port converter, basically having a low voltage DC port, high voltage DC port, and you have an AC port, and you have a ripple port. So it will manage everything with a single converter, so that you can use this as a charging, AC charging, and this is a PV panel, and this is your common battery, and you can do this active power decoupling so that the size of the entire thing will come down. And this is also patented, and we got it granted as well. We are also in discussion with some companies to commercialize this as well. And these are some modulation strategies that we need. And we are also working on technology where the onboard converter can be used for charging from 110 volt AC to 415 volt AC to charge either 400 volt battery or 800 volt battery with the same converter, onboard converter. So we are making some modifications, proposing some coupling units so that you can use this onboard converter in 5 modes: AC charging, single phase AC charging, 3-phase AC charging, DC charging, motor drive, and all X to X, like V to G, G to V, V to load, anything, like all the modes which is possible. That is what we are coming up with. Right. And coming to wireless, yes, we have working on matrix converters where you can directly convert the AC into high frequency AC with reduced number of switches, which is patented. And we are also working on how to do this reconfigurable IGBTs, where we have talked about that particular project. So the same 3-leg IGBT converter can be used for wireless charging as well. You can charge either 400 volts or 800 volts double up. So basically we are talking about voltage doubling and current doubling with a simple modification. And that is what we are trying, and this has been published in IEEE Transactions and Power Electronics. So overall we have 10 patents, 4 granted and 2 commercialized at ABB, where I contributed to that thyristor based rectification stage where you can meet the grid code without having any active or passive filter. And then some safety standards or fault detection system at ABB. And then we are working towards the commercialization of this universal motor drive charging. And we are also working on the commercialization of APD techniques as well. Okay, that's all. I hope I made the timelines. If there are any questions, please welcome, and thank you for patient listening.
Dr. Dastagiri, that was really good. Thank you for your presentation. Yeah, I really could relate a lot of things to like real life use cases.
Thank you.
Especially for the charging exam, like it related to something I know, so it was easy to understand.
Okay.
Yeah.
Any questions, please?
So we are waiting for questions.
I'm sorry that I had 1 hour, so I need to rush. I don't know whether you are able to follow or not.
We don't have any questions so far. I guess we can move on. Like even if we have more questions, we'll redirect it to you later. Yeah.
Sure.
So as we move on to the final parts, I would like to thank the students for patiently attending it. Like, I know it has been a hectic day. We've been having classes from the morning. Yeah, it has been really hard to concentrate. And I also have a notice for the students. Like as we are going forward, we have the problem statements for you guys, and we will be making them available soon. Yeah, they will have their own distinct sections to fill in the description part, the scope, and what is expected from you guys. And we'll be evaluating it, and the first shortlisting results will be coming out in around September. Yeah, and the shortlisted people like Rayleigh Motive Labs will be contacting you and then giving you personalized training and you will be able to have like deep technical conversation with the experts. Yeah, so more is coming. And also we were looking into getting the video recordings available to you guys. So once we get a green flag from all the presenters, we will also be able to share the videos with you guys. So for the final part, I would like to welcome Dr. Vasanthi for the closing remarks. Oh, is she not available? Dr. Vasanthi?
It looks like she's not available. Okay, then in that case, I would like to then welcome our very own Mr. Prashant. Oh, okay. Actually, Vasanthi ma'am is here, I believe then. Dr. Vasanthi, are you here?
It seems like some network issue so far. So we'll go to Prashant. Any final words? Can you hear us?
I think we have to unmute him. Yeah, okay. I think it's all right.
Yeah. Thanks, friends. It's a long day. I saw some 575 participants or 600 participants. Now we have close to 400. Yeah. So I really appreciate this 400 people who stayed throughout the day. Yeah. And something really make make for you. Yeah. You have a great career. Yeah. Because you are curious. You stayed throughout the day. And I respect your time. Yeah. And it's a beautiful workshop today. Yeah, I respect all the professors and also the scientists who came here and the industry leaders who came here and given you a detailed session. Of course, we cannot build a complete EV or a product in a day or so, but we can attempt what best can be done. So this, like Jason was pointing out, this is a boot camp. Yeah, it's a trigger. It's your start. You will have all the things, and additionally, we have also requested the vendor for this particular event. I think Relay Automotive Labs to help you with some mentoring. Yeah, so they will be addressing some questions and also guiding you through some product development or on your problem statements. Yeah, and Jason and Amaya, Praveen, Aaron, everyone would be there with you throughout the event. Yeah, feel free to contact them. We'll be very open to help you out. Yeah, provided you show the commitment and passion, and we are there for you. Yeah, so thank you, friends. Yeah, I'm not extending beyond. It's a privilege to discuss with you and share some ideas and meet you virtually, and looking forward for the best 10 teams, yeah, who comes and joins us at Bosch and works with us for defining the future mobility. Thank you, friends. Thank you, organizers, and thank you, eminent speakers. Yeah, bye, and have a nice weekend.
Thanks a lot, Prashant.